Welcome back to the quiet between the stars. I hope you are settled in somewhere comfortable, because tonight we are going further than we have ever gone before. Consider this. The space between galaxies is not truly empty. It contains roughly 1 atom per cubic meter, a loneliness so profound that a single hydrogen atom might drift for millions of years before encountering another. And yet, there are places in our universe where even this sparse existence thins to almost nothing at all. These are the cosmic voids, regions spanning hundreds of millions of light years, where darkness stretches unbroken, where the very fabric of space seems to hold its breath. Tonight, we begin our journey here, in the familiar glow of our own Milky Way galaxy, nestled within the Orion Spur, approximately 26,000 light years from the supermassive black hole at our galactic center. From this starting point, we will drift outward, past the gravitational embrace of our local group, beyond the Virgo Supercluster, and into the vast emptiness that makes up most of our observable universe. We will travel to the Boötes Void, a spherical region of near-nothingness stretching 330 million light-years across. If these quiet explorations help you find rest, or if the science of the cosmos brings you the same calm it brings me, please consider liking this video and subscribing to the channel. Your support allows these journeys to continue. Now let your breathing slow. Let your thoughts settle like dust in the space between stars. We are leaving Earth behind, rising gently through the atmosphere and beginning our long voyage into the deep. In the year 1933, a Swiss astronomer named Fritz Zwicky turned his attention to a gathering of galaxies some 320 million light-years from Earth. The Coma Cluster, as it was known, contained over 1,000 galaxies bound together by gravity, swirling around a common center like a vast celestial carousel. Zwicky, working at the California Institute of Technology, had developed a method to weigh this enormous structure, and what he found would haunt astronomy for decades. The technique was elegant in its simplicity. By measuring the speeds at which individual galaxies moved within the cluster, Zwicky could calculate how much gravitational pull was needed to keep them from flying apart. The physics was straightforward, rooted in principles Isaac Newton had established centuries earlier. If you know how fast something is moving in orbit, you can determine the mass of whatever is holding it in place. A planet orbiting quickly must be gripped by a massive star. A galaxy moving at tremendous speed must be bound by tremendous gravity. Zwicky measured the velocities of galaxies in the Coma Cluster using the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes. Light from galaxies moving toward us shifts slightly toward the blue end of the spectrum. Light from galaxies moving away shifts toward red. By carefully analyzing these shifts, Zwicky determined that galaxies in the Coma Cluster were racing around at approximately 1,000 kilometers per second. Some moved even faster, reaching velocities of nearly 2,000 kilometers per second relative to the cluster's center. These speeds were far too high. When Zwicky calculated the mass required to gravitationally bind galaxies moving at such velocities, he arrived at a number that made no sense. The cluster needed to contain roughly 400 times more mass than what he could see in the form of luminous galaxies. The visible matter all those billions of stars blazing across the electromagnetic spectrum accounted for less than 1% of what the gravitational arithmetic demanded. Zwicky called this discrepancy Dunkelmaterie, German for dark matter. The name was not meant to be mysterious or poetic. It was simply descriptive. Whatever was providing the missing gravity did not emit light. It was dark in the most literal sense, invisible to telescopes, detectable only through its gravitational influence on things that could be seen. The calculation relied on what physicists call the virial theorem, a relationship between the kinetic energy of moving objects and the gravitational potential energy binding them together. For a system in equilibrium, one that has settled into a stable configuration over time, these two quantities maintain a specific ratio. The Coma cluster, having existed for billions of years, had certainly reached such equilibrium. Its galaxies were not collapsing inward or dispersing outward. They were orbiting, generation after generation, held in a gravitational embrace that should have been explicable. Yet the numbers refused to cooperate. Zwicky estimated the visible mass of the cluster by counting galaxies and estimating their individual masses based on their brightness. A galaxy containing 100 billion stars, each roughly similar to our Sun, should have a mass of about 200 billion solar masses. Multiply this by the 1,000+ galaxies in the Coma cluster, and you arrive at a total visible mass on the order of 10 to the 13th solar masses. But the velocities demanded a gravitational mass closer to 10 to the 15th solar masses. The discrepancy was not subtle. It was a factor of hundreds. At the time, many astronomers dismissed Zwicky's findings. Perhaps his velocity measurements were flawed. Perhaps the cluster was not truly in equilibrium, but was instead in the process of flying apart, a temporary congregation of galaxies that would soon disperse. Perhaps the mass-to-light ratios he used to estimate galaxy masses were incorrect. The astronomical community was not ready to accept that the universe contained vast quantities of invisible matter. Zwicky himself was a difficult personality, brilliant but abrasive, prone to calling his colleagues spherical bastards, a term he explained by noting they were bastards no matter which way you looked at them. His combative nature may have contributed to the slow acceptance of his ideas, but the evidence he uncovered was real, and it would not go away. The Coma cluster sits in the constellation Coma Berenices, a relatively sparse region of the northern sky. It is one of the richest nearby clusters, a laboratory for studying how galaxies interact when crowded together by gravity. At its heart lies a pair of giant elliptical galaxies, NGC 4889 and NGC 4874, each containing trillions of stars. These central giants have grown fat by cannibalizing smaller galaxies that wandered too close, their gravity stripping stars and gas from unfortunate neighbors. Between the galaxies floats a diffuse haze of extremely hot gas, heated to temperatures exceeding 100 million degrees Kelvin. This intracluster medium, as astronomers call it, emits X-rays as electrons spiral through magnetic fields and collide with ions. Modern X-ray telescopes have mapped this gas in exquisite detail, revealing that it contains several times more mass than all the galaxies combined. Yet even adding this hot gas to the visible mass budget leaves the cluster profoundly underweight. The dark matter problem does not disappear. It merely becomes slightly less severe. Zwicky's observation planted a seed that would take 4 decades to germinate. The missing mass problem, as it came to be known, lurked at the edges of astronomical consciousness, an unsolved puzzle that most researchers preferred to ignore. The universe, it seemed, was hiding something fundamental, something that outweighed everything we could see by an enormous margin. The darkness was not empty. It was full of something with mass and gravity but no light, something that shaped the cosmos while remaining stubbornly invisible. 4 decades passed, and the missing mass problem remained precisely that, missing from the mainstream of astronomical thought. Zwicky's calculations were too strange, too inconvenient, too far removed from the comfortable physics of stars and planets. But in the 1970s, a patient astronomer in Washington, D.C., began measuring something that would force the universe to reveal its secrets once again. Vera Rubin worked at the Carnegie Institution, studying the rotation of spiral galaxies with a precision that had never before been possible. Her instrument was a new kind of spectrograph, designed by her colleague Kent Ford, capable of detecting the faint light from the outer edges of galaxies where stars grew sparse and dim. What she sought was simple in concept. Measure how fast different parts of a galaxy rotate around its center, and from those speeds calculate the distribution of mass within. The physics behind this measurement stretches back to Isaac Newton and Johannes Kepler. When an object orbits a central mass, its speed depends on how much mass lies interior to its orbit. Mercury, closest to the Sun, races around at 47 kilometers per second. Neptune, far out in the cold darkness, drifts along at a mere 5 kilometers per second. This relationship, known as Keplerian motion, predicts that orbital velocity should decrease with distance from the center of any gravitating system. The farther out you go, the slower things should move. Rubin expected to find exactly this pattern in spiral galaxies. Near the center, where stars crowd together in brilliant bulges containing billions of suns, rotation speeds should be high. Moving outward through the spiral arms, where stellar density drops and the gravitational pull weakens, speeds should decline in a graceful curve toward zero. This was the prediction. This was what every textbook said should happen. The Andromeda Galaxy became her first detailed subject. Located 2.5 million light-years away, Andromeda is the nearest large spiral to our own Milky Way, spanning some 220,000 light-years in diameter. Rubin and Ford measured the Doppler shifts of hydrogen gas clouds and star-forming regions at various distances from Andromeda's core. The Doppler effect causes light from approaching objects to shift toward blue wavelengths, while light from receding objects shifts toward red. By measuring these shifts with extreme precision, Rubin could determine velocities to within a few kilometers per second. The results defied expectation. Near Andromeda's center, stars and gas orbited at roughly 200 kilometers per second, exactly as predicted. But moving outward, the rotation curve refused to fall. At 10,000 light-years from the center, the speed remained 200 kilometers per second. At 20,000 light-years, still 200 kilometers per second. At 50,000 light-years, where the visible disk of the galaxy faded into darkness and almost no stars remained to be seen, the rotation speed held steady at 200 kilometers per second. This was impossible according to standard physics, unless the visible galaxy was embedded in something much larger and much more massive than the stars alone. Rubin turned to other galaxies. She measured the rotation curves of dozens of spirals, then hundreds. Galaxy after galaxy told the same story. The rotation curves rose steeply near the center, then flattened out and stayed flat to the very edge of detectability. In some cases, she could trace rotation speeds out to distances where the light from stars had faded to almost nothing, yet the orbital velocities remained stubbornly high. The pattern was universal. Consider what this means in terms of mass. If a star at the edge of a galaxy orbits at 200 kilometers per second, when Keplerian physics predicts it should orbit at 50 kilometers per second, then the galaxy must contain 16 times more mass than the visible matter suggests. The square of velocity enters the gravitational equations, so doubling the speed requires quadrupling the enclosed mass. The flat rotation curves implied that galaxies were surrounded by enormous halos of invisible matter, extending far beyond their visible boundaries. Rubin calculated that typical spiral galaxies contain roughly 10 times more dark matter than luminous matter. The stars, the gas, the dust, everything that emits or absorbs light accounts for perhaps 10% of a galaxy's total mass. The remaining 90% exists in some form that neither emits nor absorbs electromagnetic radiation at any wavelength. The scientific community initially resisted these findings. Perhaps the measurements were wrong. Perhaps the spectrograph introduced systematic errors. Perhaps the galaxies were not in equilibrium, their outer regions still falling inward or flying apart. Rubin addressed each objection methodically. She improved her instruments. She observed more galaxies. She demonstrated that the flat rotation curves persisted regardless of galaxy size, brightness, or morphology. Dwarf galaxies with only 1 billion stars showed flat rotation curves. Giant galaxies with 1 trillion stars showed flat rotation curves. The phenomenon was not a fluke. It was a fundamental property of galaxies themselves. By 1980, the evidence had become overwhelming. Rubin published a landmark paper analyzing 21 spiral galaxies, each one displaying the same anomalous rotation pattern. The data spoke with a clarity that could not be dismissed. Galaxies do not obey the gravitational laws implied by their visible matter alone. Something else is there, something massive and dark, something that dominates the gravitational dynamics while remaining utterly invisible to every telescope ever built. The connection to Zwicky's work became apparent. The missing mass in galaxy clusters and the missing mass in individual galaxies were manifestations of the same phenomenon. Dark matter, as it came to be called, existed at every scale where gravity could be measured with sufficient precision. It formed invisible scaffolding upon which the luminous universe was built. Rubin herself remained cautious about the interpretation. She reported what she observed: flat rotation curves extending to the limits of detection, and left the theoretical explanations to others. But the implication was inescapable. The universe contained a form of matter that interacted gravitationally, but not electromagnetically. It pulled on stars and gas with the same force as ordinary matter, yet it produced no light, reflected no light, and absorbed no light. It was there, shaping the cosmos, yet fundamentally invisible. The rotation curve anomaly transformed dark matter from an obscure puzzle into a central problem of modern physics. Zwicky had found the first clue as motions of galaxy clusters. Rubin found the second clue in the motions of stars within individual galaxies. Together, their observations pointed toward a universe far stranger than anyone had imagined, a universe where most of the matter exists in a form we cannot see, cannot touch, and cannot yet identify. The darkness between the stars was not empty. It was full of something with mass and gravity, something patient and pervasive, something waiting to be understood. Light travels in straight lines through empty space. This principle, fundamental to optics and geometry, guided astronomers for centuries. Yet Albert Einstein's general theory of relativity, published in 1915, revealed a deeper truth. Space itself could curve, and when space curved, light followed that curvature. Mass did not merely attract other masses, it warped the fabric of space-time, and everything traveling through that fabric, including light, bent along the warped paths. The first confirmation came during a solar eclipse in 1919, when Arthur Eddington measured the positions of stars near the sun's edge. The starlight had bent, deflected by approximately 1.75 arc-seconds, exactly as Einstein's equations predicted. The sun's mass had curved space-time, and light from distant stars had followed that curve. The universe operated not as a stage upon which objects moved, but as a dynamic medium shaped by the presence of mass and energy. This phenomenon, gravitational lensing, remained a theoretical curiosity for decades. The deflection caused by ordinary stars was too small to observe easily, and the idea of using entire galaxies as lenses seemed impractical. Yet as telescopes improved and astronomers began surveying the deep universe, strange apparitions appeared in their images. Distant quasars sometimes appeared doubled, tripled, or even quadrupled. Galaxies far behind massive clusters appeared stretched into thin arcs, their light smeared across the sky like reflections in a funhouse mirror. The physics operates through geometry. When a massive object lies between a distant light source and an observer, the mass curves the surrounding space-time. Light rays passing near the mass follow geodesics, the straightest possible paths through curved space. And these paths bend toward the mass. If the alignment is precise, light rays that would normally miss the observer get redirected towards them, creating multiple images or magnified views of the background source. The amount of bending depends directly on the total mass enclosed within the light's path. This relationship, encoded in Einstein's field equations, provides astronomers with a cosmic scale. By measuring how much light bends around a galaxy or cluster, they can calculate the total mass doing the bending. The technique works regardless of whether that mass emits light, absorbs light, or remains completely invisible. Gravitational lensing weighs the universe by its gravitational influence alone. Strong lensing occurs when the alignment is nearly perfect and the lensing mass is extremely concentrated. In these cases, background galaxies can appear as dramatic arcs, sometimes forming nearly complete rings called Einstein rings. The radius of such a ring, measured in arc-seconds, relates directly to the mass of the lens and the distances involved. A typical galaxy cluster might produce arcs with radii of 10 to 30 arc-seconds, corresponding to enclosed masses of hundreds of trillions of solar masses. Weak lensing operates more subtly. When the alignment is imperfect or the lensing mass is more diffuse, background galaxies experience only slight distortions. A circular galaxy might appear slightly elliptical, stretched tangentially around the lens. Any individual distortion is too small to distinguish from the galaxy's natural shape. But by analyzing thousands of background galaxies statistically, astronomers can map the distribution of lensing mass across the sky. The technique reveals mass concentrations that would otherwise remain completely hidden. The mathematics of weak lensing involves measuring the shear field, the pattern of tangential stretching around mass concentrations. In regions with more mass, background galaxies show greater average ellipticity aligned tangentially. By correlating these tiny distortions across millions of galaxies, surveys like the Dark Energy Survey and the Kilo Degree Survey have produced maps of the universe's mass distribution spanning hundreds of square degrees of sky. These maps revealed something remarkable. The mass traced by gravitational lensing did not match the mass traced by visible light. Galaxy clusters showed lensing signals far stronger than their luminous matter could produce. The total mass inferred from lensing exceeded the visible mass by factors of 5 to 10, consistent with the ratios Zwicky had calculated from velocity dispersions and Rubin had found from rotation curves. The invisible mass was there, bending light, warping space-time, yet producing no electromagnetic signal of its own. The distribution of this lensing mass followed a distinctive pattern. It concentrated around galaxies and clusters, forming extended halos that stretched far beyond the visible boundaries of stellar systems. A typical spiral galaxy might have a visible disk spanning 100,000 light-years, but its lensing signal indicated a dark matter halo extending 5 to 10 times farther. A vast, invisible cocoon surrounding the luminous core. Microlensing provided another window into the dark. When a compact, massive object passes directly in front of a background star, the star's light brightens temporarily as the gravitational lens focuses more light towards the observer. The duration and shape of this brightening curve reveals the mass of the lensing object. Surveys monitoring millions of stars in the Magellanic Clouds and the galactic bulge detected microlensing events, but not nearly enough to account for the missing mass. The dark matter could not consist primarily of dim stellar objects like brown dwarfs, white dwarfs, or black holes of stellar mass. Something else, something not made of ordinary atoms, dominated the gravitational budget. The precision of lensing measurements improved steadily through the 1990s and 2000s. The Hubble Space Telescope, orbiting above Earth's blurring atmosphere, captured images sharp enough to resolve the fine details of lensing arcs. Spectroscopy determined the redshifts of both the lensing clusters and the background sources, allowing astronomers to calculate distances and convert angular measurements into physical masses. One cluster in particular, Abel 2218, became a laboratory for lensing studies. Located approximately 2.3 billion light-years away, This massive cluster bends light from galaxies at various distances behind it. By analyzing over 100 lensing arcs and multiple image systems, astronomers constructed a detailed mass map of the cluster's core. The total mass within the central 500 kiloparsecs exceeded 1 quadrillion solar masses, with dark matter comprising roughly 85% of that total. The geometry of gravitational lensing also enabled a new kind of cosmic measurement. The time delay between multiple images of a variable source, a quasar flickering in brightness, for instance, depends on the path lengths and the gravitational potential along each path. By measuring these delays precisely, astronomers could constrain the expansion rate of the universe, the Hubble constant, independently of other methods. The technique, called time delay cosmography, added another tool to the cosmic distance ladder. Gravitational lensing transformed dark matter from an inference based on dynamics into something almost tangible. The bending of light provided a direct measurement of mass, independent of assumptions about orbital mechanics or equilibrium states. Light from the distant universe, traveling for billions of years, carried information about every mass concentration it passed. The universe itself became a vast optical system, with dark matter halos acting as lenses scattered throughout the cosmic volume. The invisible scaffolding revealed by lensing matched the predictions of cold, dark matter simulations. Computer models tracking the gravitational collapse of dark matter from the early universe produced halos with density profiles that agreed with lensing observations. The concentration of mass toward halo centers, the extended outer regions, the substructure of smaller halos within larger ones. All these features appeared in both simulations and lensing maps. Light, the messenger that had revealed the cosmos since the first telescopes, now revealed what light itself could not illuminate. The bending of ancient photons around invisible masses wrote the signature of dark matter across the sky, a signature that patient observation and careful analysis could read. The universe contained far more than met the eye, and gravitational lensing provided the clearest proof, yet that the darkness between galaxies was not empty, but full of mass, shaping the paths of light, guiding the formation of structure, holding the cosmos together through the patient, invisible pull of gravity. The gravitational lensing maps had revealed dark matter's presence around individual galaxies and within great clusters, but a single cosmic event would provide something even more compelling. A natural experiment that separated dark matter from ordinary matter, allowing astronomers to observe each component independently. This event occurred in a system known formally as 1E0657-56, located approximately 3.7 billion light-years from Earth in the southern constellation Carina. The astronomical community would come to know it simply as the Bullet Cluster, and its significance for understanding dark matter cannot be overstated. Two galaxy clusters had collided, not in the gentle gravitational dance that would eventually merge the Milky Way with Andromeda over billions of years, but in a high-speed impact that sent one cluster punching through the other like a bullet through tissue. The smaller cluster had passed through the larger one at a velocity of approximately 500 kilometers per second, among the fastest collision speeds ever observed in the universe. This impact had occurred roughly 150 million years ago, and the aftermath remained visible, frozen in cosmic time for astronomers to study. Galaxy clusters contain three primary components: the galaxies themselves, the luminous collections of stars that give clusters their name, comprise only about 2% of the total mass. The hot gas between galaxies, known as the intracluster medium, accounts for roughly 12 to 15%. This gas, heated to temperatures between 10 million and 100 million Kelvin, glows brightly in X-ray wavelengths, making it visible to space-based observatories like the Chandra X-ray telescope. The remaining 83 to 86% of cluster mass, according to gravitational measurements, consists of dark matter, invisible, undetectable except through its gravitational influence. When the two clusters collided, each component behaved according to its physical nature. The galaxies, separated by vast distances averaging several 100,000 light-years, even within clusters, passed through one another like two swarms of bees, interpenetrating without collision. Individual galaxies experienced gravitational tugs from their neighbors, but direct impacts between stellar systems remained extraordinarily rare. The galaxies emerged from the collision largely unscathed, their trajectories bent, but their structures intact. The hot gas told a different story. Unlike the widely separated galaxies, the intracluster medium filled the space between stars with diffuse but continuous plasma. When the gas clouds of the two clusters met, they could not pass through one another. Instead, they collided directly, experiencing ram pressure that slowed their motion dramatically. The gas from the smaller cluster, moving at thousands of kilometers per second, slammed into the gas of the larger cluster and decelerated. Shock waves propagated through the plasma, heating it further and creating distinctive structures visible in X-ray observations. The Chandra telescope captured these features with remarkable clarity. A bow shock ahead of the smaller cluster's gas, trailing streamers of heated plasma, the characteristic bullet shape that gave the system its name. The dark matter, if it existed as theorized, should have behaved like the galaxies rather than the gas. Dark matter particles, whatever their nature, interact through gravity, but not through the electromagnetic force that governs collisions between ordinary matter. Two dark matter particles could pass within atomic distances of one another and continue unimpeded, feeling only the weak pull of gravity. When the dark matter halos of the two clusters met, they should have interpenetrated freely, continuing along their original trajectories, while the gas lagged behind. Gravitational lensing provided the means to test this prediction. By mapping the distortion of background galaxies behind the bullet cluster, astronomers could determine where the mass actually resided, not where the visible matter appeared, but where gravity bent space-time most strongly. The observations, published in 2006 by Douglas Clow and collaborators, delivered a result of profound importance. The mass concentrations, as revealed by lensing, did not coincide with the X-ray emission from the hot gas. Instead, the gravitational mass had separated from the ordinary matter, traveling ahead with the galaxies while the gas remained behind. The spatial offset was unmistakable. The centers of mass for each cluster component, determined through careful lensing analysis, lay approximately 720,000 light-years ahead of the corresponding gas concentrations. The dark matter had passed through the collision unimpeded, just as theory predicted. The gas, slowed by electromagnetic interactions, had fallen behind. For the first time, astronomers could point to a location in the sky and say with confidence, "There lies dark matter, distinct from and separated from the ordinary matter we can see directly." This observation addressed one of the persistent alternative explanations for galactic rotation curves and cluster dynamics. Some physicists had proposed that no dark matter existed at all, that instead the laws of gravity required modification at large scales. These modified Newtonian dynamics theories, or MOND, suggested that gravity behaved differently when accelerations dropped below a certain threshold, approximately 1.2 times 10 to the negative 10th meters per second squared. Such modifications could explain rotation curves without invoking invisible mass. The bullet cluster posed severe difficulties for these alternatives. If gravity alone explained the dynamics, then the gravitational lensing should trace the distribution of visible matter, the gas that dominated the baryonic mass of each cluster. Instead, the lensing traced something else entirely, something that had separated from the gas during the collision. Modified gravity theories struggled to explain how the gravitational field could detach from its source and travel independently through space. The mass was not where the matter was. Something invisible carried the gravitational influence, and that something had passed through the collision while ordinary matter could not. Subsequent observations strengthened the case. The Chandra X-ray data revealed the temperature structure of the shocked gas, confirming collision velocities consistent with the observed separation. Weak lensing measurements from multiple telescopes and multiple background galaxy populations all pointed to the same mass distribution. The statistical significance of the offset between mass and gas exceeded 8 sigma, a probability of random occurrence so small as to be effectively zero. Other colliding clusters soon joined the bullet cluster as evidence. The system MAX J0025.4-1222, observed in 2008, showed similar separation between dark matter and hot gas following a collision. The Musketball cluster, Abell 520, and the Trainwreck cluster each provided additional examples, though some displayed more complex geometries that required careful modeling to interpret. The pattern repeated across the observable universe. When clusters collided, dark matter and ordinary matter parted ways, each following the physics appropriate to its nature. The bullet cluster observations also constrained the properties of dark matter particles themselves. If dark matter interacted with itself through some force beyond gravity, if dark matter particles could collide and scatter off one another, then the dark matter halos would have experienced drag during the cluster collision, similar to the gas. The clean separation observed implied that dark matter self-interactions must be weak, with a cross-section less than approximately 1.25 square centimeters per gram of dark matter. This constraint ruled out certain theoretical candidates while remaining consistent with the leading possibilities. The mass-to-light ratio in the bullet cluster reached extreme values. In the regions where dark matter dominated, Far from the concentrated gas, the ratio exceeded 300 solar masses per solar luminosity. The gravitational mass present in these regions outweighed the visible matter by a factor of hundreds. No known form of ordinary matter, no cold gas, no failed stars, no planetary debris could hide in such quantities without detection. The dark matter was genuinely dark, transparent to electromagnetic radiation across the entire spectrum from radio waves to gamma rays. Temperature measurements of the shocked gas provided independent confirmation of the collision dynamics. The gas temperature behind the bow shock reached approximately 160 million Kelvin, consistent with the kinetic energy of a 4,500 km per second impact being converted to thermal energy. These temperatures matched predictions from hydrodynamic simulations that included both ordinary matter and dark matter components, further validating the physical picture. The Boötes cluster became an icon of dark matter research, reproduced in countless presentations, textbooks, and popular accounts. The false color images, X-ray emission shown in pink, gravitational mass shown in blue, illustrated the separation with immediate visual impact. Here was dark matter made visible, not through its own light, but through its gravitational shadow, its influence on the fabric of space-time itself. The blue clouds of mass floated ahead of the pink clouds of gas, a cosmic demonstration of physics operating at scales and energies beyond any laboratory experiment. The implications extended beyond mere detection. The Boötes cluster showed that dark matter behaved as a collisionless fluid, responding to gravity but immune to the electromagnetic and strong nuclear forces that governed ordinary matter. This behavior matched the predictions of cold, dark matter models, in which dark matter particles moved slowly compared to light and clumped together under gravitational attraction. Hot, dark matter, composed of fast-moving particles like neutrinos, would have spread out more diffusely and could not have maintained the concentrated halos observed through lensing. The collision had occurred 150 million years ago, when dinosaurs still walked the Earth, and the Atlantic Ocean was narrower by hundreds of kilometers. Light from that cosmic impact had traveled across the expanding universe, red-shifted by the stretching of space, until it reached telescopes orbiting a small planet in an unremarkable spiral galaxy. That light carried information about the invisible majority of the universe, written in the subtle distortions of background galaxies and the glow of superheated plasma. Patient observation decoded the message, revealing that darkness and light had parted ways in a collision of unimaginable violence, each continuing on its own path through the cosmos. The separation witnessed in the Boötes cluster was not an isolated phenomenon, but rather a dramatic demonstration of a structure that surrounds every galaxy in the observable universe. Each spiral, each elliptical, each irregular collection of stars exists within an invisible cocoon of dark matter extending far beyond the visible boundaries of stellar light. These structures, known as dark matter halos, form the gravitational scaffolding upon which galaxies are built, and without them, the luminous matter we observe would never have coalesced into the cosmic architecture we see today. The Milky Way provides the nearest example. Our galaxy's visible disk, That flattened spiral of approximately 200 billion stars spans roughly 100,000 light-years from edge to edge. The disk contains the familiar spiral arms, the central bulge, the globular clusters orbiting above and below the galactic plane. Yet this visible structure represents only a small fraction of the galaxy's total extent. The dark matter halo surrounding the Milky Way extends outward to approximately 300,000 light-years from the galactic center, and some estimates suggest it may reach as far as 1 million light-years when including the most diffuse outer regions. The visible galaxy, impressive as it appears in photographs, sits like a luminous core embedded within a vast sphere of invisible matter. The mass ratio tells the story most clearly. The Milky Way's visible components, stars, gas, dust, planets, account for approximately 60 billion solar masses. The dark matter halo, by contrast, contains somewhere between 1 trillion and 2 trillion solar masses. For every kilogram of ordinary matter in our galaxy, between 10 and 30 kilograms of dark matter occupy the surrounding halo. The stars we see at night, the nebulae captured by telescopes, the planets orbiting distant suns, all of this represents perhaps 5% of the galaxy's total mass. The remaining 95% exists in a form that emits no light, absorbs no radiation, and reveals itself only through the gravitational influence it exerts on visible matter. The density profile of a dark matter halo follows a characteristic pattern discovered through computer simulations and confirmed through observational measurements. Near the center of a galaxy, dark matter density reaches its highest values, though the exact profile in the innermost regions remains a subject of ongoing research. Moving outward, the density decreases according to a mathematical relationship that astronomers call the Navarro-Frenk-White profile, named for the 3 researchers who first described it in 1996. This profile predicts that density falls off roughly as 1 over the distance from the center in the inner regions, transitioning to 1 over the distance cubed in the outer regions. The transition occurs at a characteristic radius that varies from galaxy to galaxy, typically measuring tens of thousands of light-years for a galaxy like the Milky Way. The shape of dark matter halos deviates from perfect spherical symmetry. Simulations consistently predict that halos should be slightly flattened, resembling oblate spheroids or even triaxial ellipsoids with 3 different axis lengths. The degree of flattening depends on the halo's formation history, the mergers it has experienced, and the angular momentum acquired during gravitational collapse. Observations of gravitational lensing around distant galaxies confirm this prediction, revealing halos that align with the orientation of the visible galaxy, but extend far beyond it in all directions. Within the main halo, smaller concentrations of dark matter orbit like satellites around a planet. These subhalos represent the remnants of smaller dark matter structures that fell into the larger halo during the hierarchical process of cosmic structure formation. The Milky Way's halo contains thousands of these subhalos, ranging from masses comparable to dwarf galaxies down to structures far too small to host any stars at all. Some of these subhalos correspond to the visible satellite galaxies orbiting the Milky Way, the large and small Magellanic Clouds, the Sagittarius Dwarf, the numerous ultra-faint dwarfs discovered in recent surveys. Others remain entirely dark, containing no baryonic matter whatsoever, invisible except for their subtle gravitational effects on nearby streams of stars. The dwarf spheroidal galaxies orbiting the Milky Way provide particularly striking evidence for dark matter halos. These small systems, containing only a few million stars, exhibit velocity dispersions far too high for their visible mass. The stars within the Draco dwarf spheroidal, for example, move with velocities suggesting the presence of approximately 100 times more mass than the stars themselves provide. The Segway 1 ultra-faint dwarf, containing only about 1,000 stars, appears to be embedded in a dark matter halo with a mass-to-light ratio exceeding 3,000, meaning the dark matter outweighs the visible matter by more than 3,000 to 1. These tiny galaxies represent the most dark, matter-dominated systems known, laboratories for studying the properties of halos with minimal contamination from baryonic physics. The formation of dark matter halos preceded the formation of galaxies themselves. In the early universe, slight density fluctuations in the dark matter distribution began to grow under gravitational attraction. Regions with slightly higher density pulled in surrounding material, growing denser still, while underdense regions became progressively emptier. Dark matter, unimpeded by radiation pressure or electromagnetic interactions, could begin this collapse process immediately after the Big Bang. Ordinary matter, still coupled to the intense radiation field, could not collapse until the universe cooled sufficiently for atoms to form, approximately 380,000 years after the beginning. By the time ordinary matter was free to fall into gravitational wells, dark matter had already constructed the framework. The halos existed first, and baryonic matter fell into them afterward, collecting at the centers where gravitational potential was deepest. Gas accumulated, cooled through radiation, and eventually fragmented into the first stars. Without the pre-existing dark matter halos to provide gravitational anchors, the ordinary matter would have remained too diffuse to form galaxies within the age of the universe. The structures we observe today, spirals and ellipticals, clusters and superclusters, all trace the underlying dark matter distribution that formed in the first few 100 million years of cosmic history. The concentration of a halo, defined as the ratio of its outer radius to its characteristic inner radius, provides information about when that halo formed. Halos that collapsed earlier, when the universe was denser, tend to be more concentrated than those that formed later. Massive cluster halos, which assembled relatively recently through the merger of smaller halos, typically show lower concentrations than the halos of individual galaxies. This relationship between concentration and formation time allows astronomers to use present-day halo properties to infer the assembly history of cosmic structures. The boundary of a dark matter halo presents a definitional challenge, as the density decreases smoothly with distance rather than ending at a sharp edge. Astronomers typically define the halo radius as the distance at which the average density falls to 200 times the critical density of the universe, or sometimes as the radius where material is just becoming gravitationally bound. By this definition, the Milky Way's halo extends to approximately 200 kiloparsecs, or roughly 650,000 light-years. Beyond this radius, matter is still falling inward, not yet incorporated into the bound halo structure. The total mass of dark matter halos scales with the luminosity of the galaxies they contain, but not in a simple linear relationship. More luminous galaxies tend to occupy more massive halos, yet the efficiency of converting baryonic matter into stars varies dramatically across the mass spectrum. Dwarf galaxies convert only a tiny fraction of their available baryons into stars, while galaxies like the Milky Way achieve somewhat higher efficiency. The most massive galaxies, paradoxically, also show reduced star formation efficiency, as energetic processes from supermassive black holes heat and expel gas that might otherwise form stars. The relationship between halo mass and stellar mass thus traces a curved path, peaking at intermediate masses and declining toward both extremes. The dark matter halos surrounding galaxies and threading through cosmic filaments represent a quarter of the universe's total energy content, yet their fundamental nature remains one of physics' deepest mysteries. Whatever substance comprises these invisible structures, it cannot be ordinary matter, the protons, neutrons, and electrons that form stars, planets, and human bodies. The evidence from multiple independent observations converges on a single conclusion. Dark matter must consist of particles that interact gravitationally but remain invisible to electromagnetic radiation. The question that has occupied particle physicists for decades is precisely what these particles might be. The constraints on dark matter candidates emerge from both astronomical observations and laboratory physics. Any viable particle must be electrically neutral, or it would scatter and emit light. It must be stable over cosmological timescales, persisting for the 13.8 billion years since the Big Bang without decaying into detectable products. It must be cold, meaning it moved slowly enough in the early universe to clump together and seed the formation of galaxies. And it must interact weakly enough with ordinary matter to have escaped detection in countless experiments, yet strongly enough, through gravity at minimum, to shape the largest structures in existence. The standard model of particle physics, that remarkably successful framework describing all known fundamental particles and forces, offers no satisfactory candidate. Neutrinos, the ghostly particles that stream through matter almost without interaction, were once considered promising. Trillions pass through every human body each second, produced by nuclear reactions in the Sun and other stars. They are electrically neutral and interact only through gravity and the weak nuclear force. Yet neutrinos fail as dark matter candidates for a fundamental reason. They are too light and too fast. With masses less than 1 electron volt, more than 500,000 times lighter than an electron, neutrinos moved at relativistic speeds in the early universe. Such hot dark matter would have smoothed out the density fluctuations needed to form galaxies, producing a universe far more uniform than the one we observe. The cosmic web of filaments and voids requires cold, dark matter, particles that were moving slowly when structure began to form. The most extensively studied candidates belong to a class called weakly interacting massive particles, known by the acronym WIMPs. These hypothetical particles would have masses ranging from roughly 10 to several thousand times the proton mass, between 10 and 10,000 giga-electron volts in the units particle physicists prefer. They would interact through the weak nuclear force, the same interaction responsible for radioactive beta decay, but with cross-sections so small that a WIMP could pass through a light year of solid lead with only a 50% chance of scattering. The appeal of WIMPs extends beyond their ability to explain astronomical observations. A remarkable numerical coincidence, sometimes called the WIMP miracle, suggests that particles with weak-scale masses and interactions would naturally produce the observed dark matter density through a process called thermal freeze-out. In the hot, dense conditions of the early universe, WIMPs would have been in thermal equilibrium with ordinary matter, constantly created and annihilated in pairs. As the universe expanded and cooled below, temperatures corresponding to the WIMP mass, roughly 10 to the 15th Kelvin, creation ceased, but annihilation continued. The WIMP density dropped exponentially until the expansion rate exceeded the annihilation rate, freezing in a relic abundance. The mathematics of this process, depending only on the expansion rate and the annihilation cross-section, predicts a density matching observations for particles with precisely weak-scale properties. Supersymmetry, a theoretical extension of the Standard Model that proposes a partner particle for every known particle, naturally provides WIMP candidates. The lightest supersymmetric particle, often the neutralino, a quantum mixture of the partners to the photon, Z boson, and Higgs boson, would be stable if a symmetry called R parity is conserved. Neutralinos with masses between 100 and 1,000 giga-electron volts would freeze out with approximately the right abundance and would scatter from atomic nuclei at rates potentially detectable by sensitive experiments. For 3 decades, the search for supersymmetric WIMPs drove both particle collider experiments and underground detection efforts. Yet nature has proven uncooperative. The Large Hadron Collider at CERN, colliding protons at energies up to 13 tera-electron volts, has found no evidence for supersymmetric particles. Direct detection experiments, growing ever more sensitive, have pushed the allowed WIMP nucleon scattering cross-section below 10 to the negative 47 square centimeters for particles around 50 giga-electron volts, 1,000,000 times smaller than early theoretical predictions. The WIMP miracle, while mathematically elegant, may simply be a coincidence rather than a signpost to new physics. Axions represent a fundamentally different approach to the dark matter problem. These particles were not invented to explain dark matter, but rather to solve a puzzle in quantum chromodynamics, the theory of the strong nuclear force. The strong force should, according to naive theoretical expectations, violate a symmetry called CP, the combination of charge conjugation and parity. Such violation would give the neutron an electric dipole moment, a separation of positive and negative charge along its spin axis. Yet experiments constrain the neutron electric dipole moment to less than 10 to the negative 26 electron centimeters, at least 10 billion times smaller than expected. In 1977, Roberto Pettei and Helen Quinn proposed a mechanism to dynamically suppress this CP violation, introducing a new symmetry that would be spontaneously broken. The breaking of this symmetry, as Steven Weinberg and Frank Wilczek independently recognized, would produce a new particle, the axion. The mass of this particle depends on the energy scale at which the Pecky-Quinn symmetry breaks. For scales around 10 to the 12 giga-electron-volts, axions would have masses around 1 microelectron-volt, roughly 1 trillion times lighter than the electron. Such extraordinarily light particles might seem unable to serve as cold, dark matter, yet axions would be produced through a mechanism entirely different from thermal freeze-out. As the universe cooled below the Pecky-Quinn symmetry breaking scale, the axion field would have settled into a random initial configuration. When temperatures dropped further, this field would begin oscillating coherently, behaving not as individual relativistic particles, but as a classical wave. These oscillations carry energy density that dilutes with cosmic expansion exactly as cold matter does. Axions produced through this misalignment mechanism would be cold despite their tiny mass, moving at speeds far below the speed of light. The interaction of axions with ordinary matter is extraordinarily feeble, suppressed by the high symmetry breaking scale. An axion passing through a magnetic field can convert to a photon, and vice versa, but the probability is vanishingly small. Detection requires magnetic fields of several Tesla maintained over meter-scale volumes, with microwave cavities tuned to resonate at the frequency corresponding to the axion mass. The Axion Dark Matter experiment, operating at the University of Washington, has searched for axion-to-photon conversion for over 2 decades, slowly scanning through the possible mass range. Recent results have excluded axions with masses between 2 and 4 microelectron volts at sensitivities reaching the theoretical predictions, yet the allowed parameter space remains vast. A third class of candidates, sterile neutrinos, occupies an intermediate position between WIMPs and axions. Ordinary neutrinos interact through the weak force, but sterile neutrinos would interact only gravitationally, mixing with their active counterparts through tiny quantum mechanical amplitudes. With masses in the kilo-electron-volt range, roughly 1,000 times heavier than ordinary neutrinos, but 1,000,000 times lighter than WIMPs, sterile neutrinos would constitute warm, dark matter, intermediate between the hot neutrinos and cold WIMPs. The production of sterile neutrinos in the early universe could occur through oscillations from active neutrinos, a mechanism proposed by Scott Dodelson and Lawrence Widrow in 1994. The resulting abundance depends on the mixing angle and mass, with larger mixing producing more dark matter. Alternatively, sterile neutrinos could be produced through the decay of heavier particles, potentially with different momentum distributions and cosmological consequences. Sterile neutrinos would not be perfectly stable. Through their mixing with active neutrinos, they could decay into an ordinary neutrino and a photon, with a lifetime potentially longer than the age of the universe, but not infinite. A sterile neutrino with a mass of 7 kilo-electron volts would produce photons with energies of 3.5 kilo-electron volts in the X-ray band. In 2014, 2 independent groups reported detecting an unidentified emission line at precisely this energy in observations of galaxy clusters and the Andromeda Galaxy. The line appeared where dark matter concentrations were highest, exactly as expected for decaying dark matter. Yet subsequent observations have yielded contradictory results, with some studies confirming the signal and others finding no evidence. The 3.5 kilo-electron-volt line remains controversial, neither definitively confirmed nor conclusively ruled out. The landscape of dark matter candidates extends beyond these three categories. Primordial black holes, formed not from stellar collapse, but from density fluctuations in the early universe, could contribute to or even constitute the dark matter. Gravitational wave observations from LIGO have constrained but not eliminated black holes with masses around 30 solar masses. Lighter primordial black holes below the mass of asteroids remain viable if they formed with the right abundance. The theoretical candidates, WIMPs, axions, sterile neutrinos, primordial black holes, represent humanity's best guesses about the invisible quarter of the universe. But guesses, however elegant, require experimental verification. And so, in abandoned mines and beneath mountain ranges across the globe, physicists have constructed some of the most sensitive instruments ever devised, waiting in the darkness for a particle that may never arrive. The logic of direct detection experiments rests on a simple premise. If dark matter particles pervade the galaxy, forming the halo that extends hundreds of thousands of light-years around the Milky Way, then Earth must be swimming through this invisible sea. Our solar system orbits the galactic center at approximately 220 kilometers per second, and the dark matter halo, while not entirely stationary, moves with different dynamics. The result is a wind of dark matter particles streaming through our planet at hundreds of kilometers per second, with roughly 100,000 particles passing through every square centimeter of Earth's surface each second, assuming WIMPs with masses around 100 times that of a proton. 100,000 particles per square centimeter per second sounds like an enormous flux, easily detectable. Yet these particles interact so weakly with ordinary matter that they pass through the entire Earth as if it were empty space. A WIMP could travel through a light-year of solid lead and emerge unscattered. The interaction cross-section, the effective target area that a nucleus presents to an incoming WIMP, is extraordinarily small, perhaps 10 to the minus 45 square centimeters, a number so tiny that direct comparison fails to convey its meaning. To detect such ghostly particles, experimenters must wait for the exceedingly rare collision between a WIMP and an atomic nucleus. When such a collision occurs, the nucleus recoils with a small amount of energy, typically between 1 and 100 kilo-electron-volts. This recoil can produce detectable signals, a tiny flash of light, a minuscule amount of heat, or a few electrons knocked free from their atoms. The challenge lies not in detecting these signals, but in distinguishing them from the overwhelming background of ordinary particles, cosmic rays, radioactive decays, and environmental contamination that produce identical signatures millions of times more frequently. The solution is to go underground. Cosmic rays, the high-energy particles that constantly bombard Earth's surface, cannot penetrate deep rock. At a depth of 1 kilometer, the cosmic ray flux drops by a factor of roughly 1 million. The Gran Sasso National Laboratory in Italy lies beneath 1,400 meters of dolomite rock in the Apennine Mountains. The Sanford Underground Research Facility occupies the former Homestake Gold Mine in South Dakota, with detectors positioned nearly 1,500 meters below the surface. The China Jinping Underground Laboratory, the deepest in the world, sits beneath 2,400 meters of marble, reducing cosmic ray backgrounds to nearly negligible levels. Yet going underground solves only part of the problem. The rock itself contains trace amounts of radioactive elements, uranium, thorium, potassium-40, that decay and emit particles capable of mimicking dark matter signals. The detector materials must be purified to extraordinary levels, with contamination measured in parts per trillion or less. The xenon used in liquid xenon detectors undergoes multiple distillation cycles to remove krypton-85, a radioactive isotope present in atmospheric xenon at concentrations of roughly 1 part per billion. Even this tiny contamination would overwhelm any potential dark matter signal. The xenon collaboration, operating at Gran Sasso, has pushed the boundaries of radio purity and sensitivity for 2 decades. Their current experiment, XENONNT, contains 5.9 metric tons of ultra-pure liquid xenon, with a central fiducial volume of 4 tons shielded from edge effects. When a particle interacts with a xenon nucleus, the recoil produces both scintillation light and ionization electrons. Photomultiplier tubes detect the initial light flash, while an electric field drifts the electrons upward to the liquid surface, where they produce a second light signal. The ratio of these 2 signals distinguishes nuclear recoils, the expected dark matter signature, from electron recoils caused by gamma rays and beta particles. After years of operation and analysis, XenonNT has detected no convincing dark matter signal. Their null result translates into an upper limit on the WIMP nucleon cross-section of approximately 10 to the -47 square centimeters for WIMPs with masses around 30 times the proton mass. This limit has improved by roughly a factor of 1,000 since the first xenon detectors operated in the early 2000s, yet dark matter remains undetected. The LX Zeppelin experiment, known as LZ, operates at the Sanford facility with 7 metric tons of liquid xenon. Commissioned in late 2022, LZ achieved first science results that matched and slightly exceeded xenon sensitivity. The 2 collaborations, operating on different continents with different teams, serve as independent checks on each other's results. Both have found nothing but background, pushing the allowed parameter space for WIMPs into an ever-narrowing corner. A different approach uses cryogenic detectors cooled to temperatures just above absolute zero. The CDMS collaboration, operating in the Sudan mine in Minnesota and later at Snow Lab in Canada, uses germanium and silicon crystals cooled to roughly 40 millikelvin. At these temperatures, even a tiny energy deposit from a nuclear recoil produces a measurable rise in temperature, detected by sensitive thermometers bonded to the crystal surface. Simultaneously, electrodes collect any ionization produced by the interaction. The ratio of heat to ionization again distinguishes nuclear recoils from electron recoils, providing powerful background rejection. The Super-CDMS experiment, the latest generation, employs crystals with masses of roughly 1 kilogram each, operated at temperatures of 15 millikelvin. Their sensitivity extends to lower WIMP masses than xenon detectors can probe, covering the range from 1 to 10 times the proton mass. Yet here too, after years of careful operation, the result is null. No dark matter particles have revealed themselves. The Dharma Libra experiment in Gran Sasso has reported a different story, one that has generated controversy for over 2 decades. Using sodium iodide crystals, Dharma searches not for individual dark matter interactions, but for an annual modulation in the total event rate. As Earth orbits the Sun, our velocity relative to the galactic dark matter halo varies. In June, Earth's orbital velocity adds to the Sun's galactic motion, increasing the dark matter wind speed. In December, the velocities partially cancel, reducing the flux. This modulation, with an amplitude of roughly 7%, should produce a corresponding variation in detection rates. Dharma has observed such a modulation with high statistical significance, over 12 standard deviations, persisting for more than 20 years of data collection. The phase and period match theoretical expectations precisely. Yet no other experiment has confirmed this signal, and the implied WIMP properties have been excluded by xenon, LZ, and other detectors by factors of thousands. The COSIN 100 experiment in South Korea, using the same sodium iodide target material as Dharma, has found no modulation after several years of operation. The ANICE experiment in Spain reports similar null results. The Dharma signal remains unexplained, likely arising from some unidentified systematic effect rather than dark matter. The persistent null results from direct detection experiments carry profound implications. If WIMPs exist with the properties predicted by supersymmetric theories, masses of 100 to 1,000 times the proton mass and interaction cross-sections near 10 to the minus 45 square centimeters, they should have been detected by now. The experiments have probed deeply into the theoretically favored parameter space and found nothing. Either WIMPs interact even more weakly than anticipated, or they do not exist at all. This absence has shifted attention toward lighter candidates. Axions, with masses perhaps 1 trillion times smaller than the proton, would not produce detectable nuclear recoils. Instead, axion searchers exploit the particle's predicted coupling to electromagnetism. The ADMX experiment at the University of Washington uses a powerful magnetic field and a resonant microwave cavity to convert axions into detectable photons. The conversion rate depends on the axion mass, so the cavity must be tuned across a range of frequencies, scanning slowly through the possible mass values. After decades of operation, ADMX has excluded axions in a narrow mass range, around 2 to 4 microelectron volts, but has not achieved a detection. The neutrino floor looms as an ultimate barrier for direct detection experiments. Neutrinos from the Sun, from atmospheric cosmic ray interactions, and from distant supernovae produce nuclear recoils indistinguishable from dark matter signals. As detectors grow larger and more sensitive, these neutrino interactions will eventually dominate the event rate, creating an irreducible background. For WIMP nucleon cross-sections below roughly 10 to the minus 48 square centimeters, neutrino events will outnumber any potential dark matter signal, requiring new techniques to distinguish the two. The hunt continues, driven by the certainty that dark matter exists and the hope that it will eventually reveal its particle nature. Larger detectors are under construction. The Darwin collaboration plans a 50-ton liquid xenon experiment, while the Global Argon Dark Matter collaboration develops a 300-ton liquid argon detector. These instruments will probe cross-sections approaching the neutrino floor, covering nearly all remaining parameter space for conventional WIMPs. Yet the possibility remains that dark matter consists of something entirely unexpected, something that leaves no trace in underground detectors regardless of their size or sensitivity. The universe is not obligated to conform to human theoretical preferences. The dark matter that shapes galaxies and bends light may interact with ordinary matter only through gravity, forever beyond the reach of particle physics experiments. In that case, the hunt underground will yield only silence, and the nature of the invisible quarter will remain hidden, known only through its gravitational shadow cast across the cosmos. The gravitational shadow may be the only signature dark matter leaves upon the cosmos, yet the universe offers another method for constraining what the invisible mass cannot be. Long before galaxies formed, before the first stars ignited, the universe itself conducted an experiment in nuclear physics, an experiment whose results remain encoded in the composition of matter everywhere we look. This primordial nucleosynthesis, occurring in the first few minutes after the Big Bang, places strict limits on how much ordinary matter the universe can contain, and those limits fall far short of the total mass required to explain galactic rotation curves and gravitational lensing. The story begins at a time almost incomprehensibly brief after the universe's origin. When the cosmos was approximately 1 second old, its temperature exceeded 10 billion Kelvin, hotter than the core of any star that would ever form. At such extreme temperatures, matter existed as a plasma of free protons, neutrons, electrons, and neutrinos, all in thermal equilibrium. The weak nuclear force maintained a balance between protons and neutrons through reactions that converted one into the other. As long as this equilibrium held, the ratio of neutrons to protons remained determined by their slight mass difference. Neutrons being approximately 1.3 mega-electron volts heavier than protons. As the universe expanded, it cooled. When the temperature dropped below approximately 1 mega-electron volt, corresponding to an age of about 1 second, the weak interactions became too slow to maintain equilibrium. The neutron-to-proton ratio froze out at roughly 1 neutron for every 6 protons. This ratio would decrease slightly over the following minutes, as free neutrons underwent beta decay, transforming into protons with a half-life of about 10 minutes. By the time nuclear fusion could begin, the ratio had dropped to approximately 1 neutron for every 7 protons. Nuclear fusion requires temperatures high enough to overcome the electromagnetic repulsion between positively charged nuclei, yet low enough that newly formed nuclei are not immediately torn apart by energetic photons. This window opened when the universe was approximately 3 minutes old, at a temperature of roughly 1 billion Kelvin. Protons and neutrons began combining to form deuterium, heavy hydrogen consisting of 1 proton and 1 neutron. Deuterium then served as a stepping stone to heavier elements, fusing with additional protons and neutrons to create helium-3 and tritium, which in turn combined to form helium-4. The process was remarkably efficient at producing helium-4. Nearly all available neutrons were incorporated into helium nuclei, each containing 2 protons and 2 neutrons. Given the 1:7 neutron-to-proton ratio, Simple arithmetic predicts that helium-4 should constitute approximately 25% of all baryonic mass, ordinary matter made of protons and neutrons. The remaining 75% would remain as hydrogen. This prediction, derived from nuclear physics and the known expansion rate of the early universe, matches observations with extraordinary precision. Measurements of helium abundance in primitive gas clouds, regions that have experienced minimal stellar processing, consistently yield values between 24 and 25% by mass. The agreement between prediction and observation represents one of the great triumphs of Big Bang cosmology. Yet the calculation depends critically on a single parameter: the density of baryons in the early universe. Higher baryon density means more frequent nuclear collisions, faster reaction rates, and different final abundances. Lower density means fewer collisions and altered outcomes. The observed abundances of light elements, not just helium-4, but also deuterium, helium-3, and lithium-7, constrain the baryon density with remarkable precision. Deuterium proves particularly sensitive to baryon density. Unlike helium-4, which represents a stable endpoint of primordial fusion, deuterium is fragile and easily destroyed. In a denser universe, more deuterium would be processed into heavier elements, leaving less behind. In a sparser universe, more deuterium would survive. Observations of deuterium in distant quasar absorption systems, clouds of pristine gas backlit by brilliant active galactic nuclei, reveal a deuterium to hydrogen ratio of approximately 2.5 parts per 100,000. This measurement, combined with nuclear reaction rates determined in laboratory experiments, constrains the baryon density to approximately 4.5% of the critical density required to make the universe geometrically flat. The critical density itself equals roughly 9.5 times 10 to the negative 27th kilograms per cubic meter, about 5 hydrogen atoms per cubic meter averaged across all space. Baryons constitute only 4.5% of this value, meaning ordinary matter amounts to roughly 1 proton for every 4 cubic meters of the universe. This figure includes all the atoms in every star, every planet, every gas cloud, every human being who has ever lived. All the matter we can see, touch, and detect through electromagnetic radiation represents less than 5% of the universe's total energy content. The constraint from nucleosynthesis is absolute. If dark matter consisted of ordinary baryonic matter, perhaps dim stars, cold gas clouds, or compact objects, the baryon density would need to be much higher than nucleosynthesis allows. The observed abundances of light elements would be impossible to explain. Deuterium would be far rarer, helium far more abundant, and the delicate agreement between theory and observation would collapse. Whatever dark matter is, it cannot be made of protons and neutrons. It cannot be ordinary matter hiding in darkness. This conclusion eliminated several early candidates for dark matter. Massive compact halo objects, or MACHOS, a category including brown dwarfs, rogue planets, and stellar remnants, cannot account for the missing mass. While such objects certainly exist, their total contribution is limited by the baryon budget established in the first 3 minutes of cosmic history. Searches for MACHOS through gravitational microlensing, which detects the brief brightening of background stars when a massive object passes in front of them, confirmed this limitation. The Eros and Macho surveys monitored millions of stars in the Magellanic Clouds throughout the 1990s, finding far fewer microlensing events than would be expected if dark matter halos consisted primarily of compact baryonic objects. The nucleosynthesis constraint also rules out primordial black holes as the dominant dark matter component, at least for black holes formed from baryonic matter. If such objects formed before nucleosynthesis from collapsing regions of ordinary matter, they would have removed baryons from the cosmic inventory, altering the predicted light element abundances. However, primordial black holes formed from other mechanisms, perhaps from density fluctuations in the very early universe, before baryons even existed, remain viable candidates, though observational constraints from various sources limit their allowed mass ranges. The precision of nucleosynthesis calculations improved dramatically over decades of research. Nuclear physicists measured reaction cross-sections with increasing accuracy, determining exactly how quickly deuterium forms, how efficiently it converts to helium, and how trace amounts of lithium-7 emerge from the primordial plasma. Astrophysicists refined their measurements of light element abundances in primitive environments, seeking gas clouds untouched by stellar nucleosynthesis. The concordance between these independent lines of evidence, laboratory nuclear physics and astronomical observation, strengthened the case that baryons constitute only a small fraction of the universe's matter content. Yet one discrepancy persists. The predicted abundance of lithium-7, based on the same physics that successfully explains hydrogen, deuterium, and helium, exceeds observed values in old, metal-poor stars by a factor of approximately 3. This lithium problem remains unresolved, with proposed explanations ranging from systematic errors in stellar abundance measurements to new physics affecting lithium production or destruction. The discrepancy is small enough that it does not undermine the overall nucleosynthesis framework, but it serves as a reminder that even our most successful theories may harbor incomplete understanding. The baryon density derived from nucleosynthesis received independent confirmation from an entirely different cosmic phenomenon: the cosmic microwave background radiation, the afterglow of the Big Bang itself. The patterns imprinted on this ancient light encode information about the early universe's composition, including the ratio of baryons to photons. Measurements from the Planck satellite yielded a baryon density of 4.9% of critical density, in remarkable agreement with nucleosynthesis constraints. Two completely independent methods, probing different epochs separated by hundreds of thousands of years, converge on the same answer. Ordinary matter is cosmically rare. That ancient light, released when the universe was merely 380,000 years old, carries within its subtle temperature variations a detailed record of conditions in the primordial cosmos. The cosmic microwave background radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson as persistent static in their radio antenna, represents the oldest electromagnetic signal accessible to observation. What began as an annoying noise that researchers initially attributed to pigeon droppings on their equipment revealed itself to be the thermal afterglow of the Big Bang, cooled by cosmic expansion from thousands of degrees to a mere 2.725 Kelvin, less than 3 degrees above absolute zero. The uniformity of this radiation across the entire sky provided early confirmation of the Big Bang model, demonstrating that the observable universe once existed in a hot, dense, remarkably homogeneous state. But within that uniformity lie tiny fluctuations, temperature differences of roughly 1 part in 100,000 that encode the seeds of all cosmic structure. These minuscule variations, first mapped in detail by the COBE satellite in 1992 and subsequently refined by WMAP and Planck, represent density perturbations in the early universe, regions slightly denser or less dense than average, that would eventually grow into galaxies, clusters, and the vast cosmic web. The physics imprinted on these temperature fluctuations operates through a mechanism called acoustic oscillation. In the epoch before the cosmic microwave background was released, the universe existed as a plasma of protons, electrons, and photons, all tightly coupled through electromagnetic interactions. Photons could not travel freely. They scattered continuously off free electrons, creating a fog that rendered the universe opaque. Within this plasma, gravity and radiation pressure engaged in a cosmic tug-of-war. Regions of higher density attracted more matter through gravitational attraction, compressing the plasma and raising its temperature. But this compression also increased radiation pressure, which pushed back against gravity, causing the overdense region to expand. The expansion reduced density and pressure, allowing gravity to dominate once more, initiating another compression. These oscillations propagated through the plasma as sound waves, pressure waves traveling at roughly 170,000 kilometers per second, about half the speed of light in that dense medium. The oscillations continued until recombination, the moment when the universe cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms. At a temperature of approximately 3,000 Kelvin, reached about 380,000 years after the Big Bang, photons suddenly found themselves in a transparent universe. They decoupled from matter and began their 13.8 billion-year journey to our detectors, carrying a snapshot of the oscillation pattern frozen at that precise moment. Some regions were caught at maximum compression, appearing slightly hotter in the cosmic microwave background. Others were caught at maximum rarefaction, appearing slightly cooler. The pattern of these frozen sound waves, when analyzed mathematically, reveals the fundamental properties of the early universe. The angular power spectrum of the cosmic microwave background, a graph showing the intensity of temperature fluctuations at different angular scales, displays a series of peaks and troughs that encode cosmic parameters with remarkable precision. The first peak, occurring at an angular scale of approximately 1 degree, corresponds to the fundamental mode of oscillation. Regions that had time for exactly 1 compression before recombination. Its position on the angular scale reveals the geometry of the universe, confirming that space is flat to within 0.4%. The height of this peak, relative to the overall fluctuation amplitude, constrains the total matter density, but it is the relationship between odd and even peaks that reveals dark matter's presence in the primordial plasma. Odd-numbered peaks represent compressions, moments when gravity has pulled matter together. Even-numbered peaks represent rarefactions, moments when radiation pressure has pushed matter apart. In a universe containing only ordinary baryonic matter, coupled to photons through electromagnetic forces, the compression and rarefaction phases would be symmetric. The odd and even peaks would have similar heights, reflecting the equal push and pull of gravity and radiation pressure on the same material. The observed power spectrum tells a different story. The odd peaks are significantly enhanced relative to the even peaks, with the first peak towering above the second, and the third peak again rising above the fourth. This asymmetry reveals the presence of matter that participates in gravitational compression but does not feel radiation pressure. Matter that is not coupled to photons because it does not interact electromagnetically. Dark matter, already falling into gravitational wells before recombination, enhanced the compression phases by adding its gravitational pull to that of the baryons. But during rarefaction, when radiation pressure pushed baryonic matter outward, the dark matter remained in place, unaffected by photon pressure. The baryons oscillated within gravitational wells that dark matter had already begun to deepen, creating the observed asymmetry between compression and rarefaction peaks. The Planck satellite, launched in 2009 and operational until 2013, measured the cosmic microwave background with unprecedented precision, mapping temperature fluctuations across the full sky with angular resolution of 5 arc-minutes and temperature sensitivity of millionths of a degree. The resulting power spectrum, with its characteristic pattern of peaks extending to angular scales smaller than 1/10 of a degree, constrains cosmological parameters to percent-level precision. The analysis yields a dark matter density of 26.8% of the universe's total energy content, compared to just 4.9% for ordinary baryonic matter. The ratio of dark matter to baryons, approximately 5.4 to 1, emerges not from galaxy rotation curves or cluster dynamics, but from the acoustic physics of the primordial plasma, an entirely independent line of evidence converging on the same conclusion. The cosmic microwave background also reveals the nature of primordial density fluctuations, the seeds from which all structure grew. The power spectrum of these initial perturbations is nearly scale invariant, meaning that fluctuations of all sizes had approximately equal amplitude when they were generated. This pattern matches predictions from cosmic inflation, a hypothetical period of exponential expansion in the universe's first fraction of a second. Quantum fluctuations, stretched to cosmic scales by inflation, provided the density variations that gravity would later amplify into galaxies and clusters. Dark matter, already present during this epoch, began responding to these perturbations immediately, while baryonic matter remained locked in its electromagnetic dance with photons until recombination freed it to fall into the gravitational wells dark matter had prepared. The polarization of the cosmic microwave background provides additional constraints on dark matter and the early universe. Photons scattering off electrons in the primordial plasma acquired slight polarization, with the polarization pattern reflecting the local velocity and density gradients at the moment of last scattering. The E-mode polarization, with its characteristic pattern around temperature hot and cold spots, confirms the acoustic oscillation picture and provides independent measurements of cosmological parameters. The B-mode polarization, generated by gravitational waves from inflation or by gravitational lensing of E-modes, offers probes of even earlier epochs and the distribution of matter along the line of sight. Gravitational lensing of the cosmic microwave background itself has emerged as a powerful tool for mapping dark matter distribution. As ancient photons travel through the universe, they pass through the gravitational fields of intervening matter concentrations, experiencing slight deflections that distort the primordial pattern. By analyzing the statistical properties of these distortions, cosmologists can reconstruct the integrated mass distribution between the surface of last scattering and the present day. The lensing signal detected by Planck and ground-based experiments like the South Pole Telescope and the Atacama Cosmology Telescope confirms the presence of dark matter structures consistent with predictions from the lambda-CDM model. The structures that gravitational lensing reveals, those vast concentrations of invisible mass stretching across hundreds of millions of light-years, did not emerge spontaneously in a universe already billions of years old. They grew from seeds planted in the first fraction of a second after the Big Bang, nurtured by the patient gravitational pull of dark matter over cosmic time. The web of filaments and clusters that defines the large-scale universe today represents the culmination of a construction project spanning 13.8 billion years, with dark matter serving as both architect and primary building material. In the earliest moments, the universe existed in a state of extraordinary uniformity. The cosmic microwave background reveals temperature variations of only 1 part in 100,000, a smoothness that seems almost incompatible with the lumpy universe we observe today, where matter concentrates in galaxies separated by vast, empty voids. The transition from that primordial smoothness to the present cosmic web required a mechanism capable of amplifying tiny initial fluctuations into the massive structures that now contain all visible matter. Dark matter provided that mechanism, beginning its gravitational work long before ordinary matter could participate. The physics of this amplification process depends critically on the different behaviors of dark matter and baryonic matter in the early universe. During the first 380,000 years, ordinary matter remained coupled to radiation through electromagnetic interactions. Photons scattered continuously off free electrons, creating a pressure that resisted gravitational collapse. Any region where baryonic matter began to concentrate would experience radiation pressure pushing outward, counteracting gravity's inward pull. This competition produced the acoustic oscillations imprinted on the cosmic microwave background, sound waves propagating through the primordial plasma at approximately 170,000 kilometers per second. Dark matter experienced no such resistance. Interacting only through gravity, it remained immune to the radiation pressure that buffeted ordinary matter. While baryons oscillated, dark matter could begin collapsing immediately, responding to the gravitational attraction of slightly overdense regions without any counterbalancing force. This head start proved decisive. By the time the universe cooled enough for electrons to combine with nuclei, the epoch of recombination that released the cosmic microwave background, dark matter had already been concentrating for hundreds of thousands of years. The initial density fluctuations that seeded this process likely originated during cosmic inflation, a period of exponential expansion in the universe's first 10 to the negative 32nd seconds. Quantum fluctuations in the inflaton field were stretched to macroscopic scales, becoming the density variations that would eventually grow into galaxies and clusters. These primordial perturbations followed a nearly scale-invariant spectrum, meaning fluctuations existed on all size scales with roughly equal amplitude relative to their wavelength. The Planck satellite measured the spectral index of these fluctuations as 0.965, slightly less than unity, a subtle tilt that carries information about the physics of inflation itself. Once inflation ended and the universe entered its radiation-dominated phase, the growth of structure proceeded according to well-understood gravitational physics. Regions with slightly higher dark matter density exerted slightly stronger gravitational attraction on their surroundings, drawing in additional material and becoming denser still. This positive feedback loop, gravitational instability, amplified initial perturbations over time. However, the growth rate depended on the universe's expansion history. During radiation domination, when the energy density of photons exceeded that of matter, expansion proceeded too rapidly for dark matter perturbations to grow efficiently. Structure formation entered a period of stagnation, with density contrasts increasing only logarithmically with time. The transition to matter domination, occurring approximately 47,000 years after the Big Bang, marked a turning point. Once dark matter's energy density exceeded that of radiation, gravitational instability could proceed more efficiently. Density perturbations began growing proportionally to the scale factor, the measure of cosmic expansion, rather than logarithmically. A region that was 0.001% overdense at matter radiation equality would become 0.1% overdense by the time the universe had expanded by a factor of 100. This linear growth phase continued for billions of years, gradually transforming the nearly uniform early universe into an increasingly structured cosmos. The mathematics of this growth follows from Newtonian gravity applied to an expanding universe. A density perturbation delta, defined as the fractional deviation from the mean density, evolves according to a second-order differential equation that balances gravitational attraction against cosmic expansion. In a matter-dominated universe with critical density, the growing solution increases as the scale factor to the power of 1, linear growth. In a universe dominated by dark energy, as ours has been for the past 5 billion years, growth slows dramatically as accelerating expansion stretches perturbations faster than gravity can amplify them. Computer simulations have become essential tools for understanding how these growing perturbations evolved into the structures we observe today. The Millennium simulation, completed in 2005, tracked the gravitational interactions of 10 billion dark matter particles within a cubic volume 2.4 billion light-years on a side, following structure formation from redshift 127 to the present. More recent simulations like Illustris TNG and EAGLE have incorporated baryonic physics, gas dynamics, star formation, supernova feedback, black hole growth, to model the full complexity of galaxy formation within dark matter halos. These simulations reveal a hierarchical process of structure formation. The smallest dark matter halos collapsed first, forming when the universe was only a few 100 million years old. These early halos, with masses perhaps 1 million times that of the Sun, may have hosted the first stars, massive, short-lived objects that enriched the universe with heavy elements before exploding as supernovae. Over time, small halos merged to form larger ones, building up the mass hierarchy through countless gravitational encounters. A galaxy cluster like Coma, containing thousands of galaxies within a dark matter halo of 10 to the 15th solar masses, assembled through the merger of hundreds of smaller groups over billions of years. The geometry of this assembly process created the cosmic web. Dark matter did not collapse uniformly in all directions, but preferentially along certain axes, forming elongated filaments that connected denser nodes. The mathematics of gravitational collapse in 3 dimensions naturally produces this web-like topology. A region that is overdense along one axis will collapse first along that direction, forming a sheet. Collapse along a second axis produces a filament. Only when all 3 axes have collapsed does a roughly spherical halo form. The cosmic web thus represents different stages of gravitational collapse, frozen at different locations. Voids where collapse has barely begun, walls where one-dimensional collapse has occurred, filaments where 2-dimensional collapse is complete, and clusters where full 3-dimensional collapse has produced bound structures. Observations confirm this theoretical picture with remarkable precision. Galaxy redshift surveys like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, revealing the filamentary structure predicted by dark matter simulations. The distribution of galaxies traces the underlying dark matter distribution, though with some bias. Galaxies preferentially form in the densest regions of dark matter halos, making them imperfect but useful traces of the invisible scaffolding. The correlation function of galaxy positions, a statistical measure of how likely galaxies are to be found at various separations, matches predictions from lambda CDM cosmology across scales from 1 megaparsec to several hundred megaparsecs. At 150 megaparsecs, a subtle enhancement in the correlation function appears, the baryon acoustic oscillation feature, a relic of the sound waves that propagated through the early universe. This feature serves as a standard ruler for measuring cosmic distances and confirms that the same physics governing the cosmic microwave background also shaped the distribution of galaxies billions of years later. Without dark matter, this entire construction process would have failed. Baryonic matter alone, released from radiation pressure only at recombination, would have had insufficient time to grow the observed structures. The density perturbations in ordinary matter at that epoch were only about 1 part in 100,000. Growing linearly from redshift 1100 to the present, a factor of 1100 in scale factor, would amplify these perturbations to only about 1%. Yet galaxies represent density contrasts of millions relative to the cosmic mean. The additional growth provided by dark matter's early start, combined with the gravitational wells it created for baryons to fall into, bridges this gap between primordial smoothness and present-day structure. The gravitational architecture that dark matter constructed over billions of years, those filaments and nodes and vast cosmic voids, seemed to represent a complete picture of how the universe evolved from primordial smoothness to present complexity. Yet this understanding contained a hidden assumption, one that astronomers of the late 20th century would discover to be profoundly incorrect. The assumption was simple, that the expansion of the universe, while ongoing, must be gradually slowing down. This expectation arose from basic physics. The universe contains matter, and matter generates gravity, and gravity attracts. Every galaxy pulls on every other galaxy across the cosmic web. This mutual attraction should act as a brake on the expansion that began with the Big Bang, gradually decelerating the outward rush of space itself. The only question seemed to be how quickly this deceleration was occurring, and whether it would eventually halt expansion entirely, perhaps even reverse it into a final collapse. Measuring this deceleration required looking backward in time, which in astronomy means looking outward in space. Light from distant objects shows us those objects as they were when the light departed, and the most distant observable sources reveal conditions billions of years in the past. If the expansion rate has been changing, then comparing the apparent brightness and redshift of objects at different distances should reveal the history of that change. Objects that emitted their light when the universe was expanding faster should appear at different distances than objects that emitted when expansion had slowed. The challenge lay in finding objects whose intrinsic brightness was known with sufficient precision. Without knowing how luminous a source truly is, its apparent brightness reveals nothing about its distance. A dim nearby candle and a brilliant distant searchlight might appear equally bright in the sky. Astronomers needed what they called standard candles, objects of known luminosity that could serve as cosmic distance markers. Two research teams formed in the 1990s to pursue this measurement using a particular type of stellar explosion. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, began systematic searches in 1988. The High-Z Supernova Search Team, led by Brian Schmidt at Mount Stromlo Observatory, with Adam Rees conducting crucial analysis, formed in 1994. Both groups targeted type Ia supernovae, thermonuclear explosions of white dwarf stars that offered remarkable consistency in their peak luminosity. These explosions occur when a white dwarf, the dense remnant core of a sun-like star, composed primarily of carbon and oxygen and supported against gravity by electron degeneracy pressure, accumulates matter from a companion star or merges with another white dwarf. When the white dwarf's mass approaches the Chandrasekhar limit of approximately 1.4 solar masses, the pressure and temperature in its core become sufficient to ignite runaway carbon fusion. Unlike fusion in normal stars, which is regulated by expansion and cooling, fusion in a degenerate white dwarf proceeds explosively. The entire star detonates within seconds, releasing energy equivalent to several billion suns and briefly outshining its entire host galaxy. The consistency of this process, always the same mass limit, always the same fuel, always the same explosive mechanism, produces explosions of remarkably uniform intrinsic brightness. Type Ia supernovae reach peak absolute magnitudes of approximately -19.3, with variations that can be calibrated using the relationship between peak brightness and the rate at which the supernova fades. Brighter explosions decline more slowly, dimmer ones more quickly, and this correlation allows astronomers to standardize the luminosities to within about 7% precision. Both teams developed sophisticated techniques for discovering these rare events in distant galaxies. A typical galaxy hosts only 1 or 2 Type Ia supernovae per century, so finding them required monitoring thousands of galaxies simultaneously, comparing images taken weeks apart to identify new points of light. The Supernova Cosmology Project pioneered the strategy of scheduled searches timed to guarantee telescope access for follow-up observations, transforming supernova cosmology from opportunistic discovery to systematic science. By the late 1990s, both teams had accumulated sufficient data to constrain the deceleration parameter, the quantity that described how quickly the expansion was slowing. The expected result, based on the known matter content of the universe, was a gradual deceleration. The actual result defied all expectations. The distant supernovae appeared fainter than they should have been, not by small amounts attributable to measurement error or dust absorption, but systematically and significantly fainter across the entire sample. Supernovae at redshifts around 0.5, meaning their light had been stretched by 50% during its journey, corresponding to distances of roughly 5 billion light-years, appeared about 25% dimmer than a decelerating universe would predict. Fainter meant farther, and farther, at a given redshift, meant that the expansion had not been slowing down. It had been speeding up. The two teams, working independently with different telescopes, different analysis methods, and different samples of supernovae, reached the same conclusion in 1998. The universe's expansion was accelerating. Something was pushing galaxies apart faster and faster, overwhelming the gravitational attraction of all the matter in the cosmos. The initial reaction within the scientific community combined astonishment with skepticism. Accelerating expansion required some form of energy with negative pressure, a concept that seemed to violate intuition about how energy and pressure should behave. Normal matter and radiation both produce positive pressure, which in general relativity contributes to gravitational attraction. Acceleration required something that pushed rather than pulled, something that grew stronger as space expanded rather than diluting like ordinary matter. Both teams subjected their results to exhaustive scrutiny. Could dust in distant galaxies be absorbing supernova light, making them appear artificially dim? Analysis of supernova colors argued against this. Dust absorption would redden the light in characteristic ways that were not observed. Could distant supernovae be intrinsically different from nearby ones? Perhaps because the stars that produced them formed from primordial gas with different chemical composition. Detailed spectroscopic comparisons showed the explosions to be remarkably similar across cosmic time. Could gravitational lensing by intervening matter be systematically demagnifying the distant sources? Statistical analysis demonstrated that lensing effects averaged out across large samples and could not explain the systematic dimming. The evidence accumulated and solidified. Additional supernovae discovered at even greater distances, redshifts approaching and exceeding 1.0, corresponding to light travel times of 8 billion years or more, revealed that the acceleration had not always dominated. In the early universe, when matter was more densely concentrated, gravity had indeed been slowing the expansion. The transition from deceleration to acceleration occurred roughly 5 billion years ago, when the universe was about 9 billion years old. Before that transition, matter's gravity dominated. After it, something else took over. This something else came to be called dark energy, a name that acknowledged both its mysterious nature and its kinship with the equally mysterious dark matter. Yet dark energy behaved nothing like dark matter. Dark matter clumped, forming halos around galaxies and concentrating in the nodes of the cosmic web. Dark energy appeared to be perfectly uniform, the same density everywhere in space, unaffected by the presence or absence of matter. Dark matter's gravitational effects attracted. Dark energy's effects repelled. The discovery earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics, recognition of a finding that fundamentally altered humanity's understanding of cosmic evolution. The universe was not merely expanding, it was expanding at an ever-increasing rate, driven by an energy whose nature remained completely unknown. The careful measurement of exploding stars billions of light-years distant had revealed that the majority of the universe's energy content existed in a form that physics could not yet explain, a form that would determine the ultimate fate of every galaxy, every star, every atom in the cosmos. The exploding stars that revealed cosmic acceleration possessed a peculiar property that made them uniquely valuable for measuring the universe's expansion history. Type Ia supernovae, unlike the core collapse explosions of massive stars, followed a remarkably consistent pattern. Their peak brightness varied by only about 15% from one event to another, and even that variation could be corrected through careful observation of how quickly each supernova faded after maximum light. This consistency arose from the physics of their origin. A type Ia supernova occurs when a white dwarf, the dense Earth-sized remnant of a sun-like star, accumulates material from a companion until it approaches a critical threshold. That threshold, known as the Chandrasekhar limit, sits at approximately 1.4 solar masses, the maximum weight that electron degeneracy pressure can support against gravitational collapse. As the white dwarf nears this limit, carbon and oxygen nuclei in its interior begin fusing in a runaway thermonuclear reaction. The explosion releases approximately 1 to 2 times 10 to the 43 joules of energy, roughly equivalent to the total energy output of the Sun over its entire 10 billion-year lifetime, compressed into a few seconds. The consistency of the Chandrasekhar limit means that every Type Ia supernova begins from nearly identical initial conditions, the same mass, the same composition, the same trigger mechanism. This uniformity translates into predictable luminosity. At peak brightness, a typical Type Ia supernova radiates with an absolute magnitude of approximately negative 19.3, meaning it shines with the light of roughly 5 billion suns. This extraordinary luminosity makes these explosions visible across billions of light years, beacons bright enough to outshine their entire host galaxies for several weeks. The combination of extreme brightness and consistent output creates what astronomers call a standard candle, an object whose intrinsic luminosity is known, allowing its distance to be calculated from how bright it appears. The principle underlying this measurement dates back centuries to the inverse square law of light propagation. A candle twice as far away appears 4 times dimmer. A supernova at 1 billion light-years appears 100 times fainter than an identical supernova at 100 million light-years. By comparing the observed brightness of a Type Ia supernova to its known intrinsic luminosity, astronomers can calculate how far the light has traveled to reach Earth. The technique required refinement before it could reveal cosmic acceleration. In the early 1990s, astronomers Mark Phillips discovered a crucial correlation. Brighter Type Ia supernovae decline more slowly from their peak luminosity than fainter ones. A supernova that takes 15 days to fade by 1 magnitude in brightness will have reached a higher peak luminosity than one that fades in 11 days. This relationship, now called the Phillips relation, allows astronomers to standardize supernova brightness with remarkable precision. After applying this correction, the scatter in Type Ia peak luminosities drops to roughly 7%. Additional corrections account for the color of the supernova. Redder events tend to be either intrinsically fainter or obscured by dust, and the properties of the host galaxy. With all corrections applied, Type Ia supernovae become distance indicators accurate to approximately 5%, precise enough to detect the subtle effects of cosmic acceleration. The Supernova Cosmology Project and the High-Z Supernova Search Team employed sophisticated techniques to find these rare events. A Type Ia supernova occurs roughly once per century in a typical galaxy, making them extraordinarily uncommon in any single location. But the observable universe contains hundreds of billions of galaxies, meaning that at any moment, thousands of Type Ia supernovae are exploding somewhere within the range of modern telescopes. The search strategy involved imaging the same patches of sky repeatedly, comparing new observations to reference images taken weeks earlier. Any new point of light that appeared in or near a galaxy became a supernova candidate. The teams used the 4-meter Blanco telescope at Cerro Tololo in Chile and the Canada-France-Hawaii telescope on Mauna Kea, instruments capable of surveying large areas of sky while detecting faint, distant sources. Once candidates were identified, spectroscopic observations confirmed their nature. The spectrum of a Type Ia supernova shows characteristic absorption features from silicon, sulfur, and calcium, elements synthesized in the thermonuclear explosion. The silicon absorption line near 6,150 angstroms became the defining signature, distinguishing Type Ia events from core collapse supernovae that show hydrogen in their spectra. The same spectrum that confirmed a supernova's type also revealed its redshift. As light travels through expanding space, its wavelength stretches proportionally to how much the universe has expanded since the light was emitted. A supernova whose light has been traveling for 7 billion years shows spectral features shifted toward longer wavelengths by approximately 70%. a redshift of 0.7 in astronomical notation. The crucial measurement combined these two pieces of information: the distance calculated from the supernova's apparent brightness and the redshift measured from its spectrum. In a universe expanding at a constant rate, these quantities would follow a simple linear relationship. More distant supernovae would show proportionally higher redshifts. In a decelerating universe where gravity was slowing the expansion, distant supernovae would appear slightly brighter than this linear prediction, because the universe was expanding faster in the past. What the observations revealed contradicted both expectations. Supernovae at redshifts around 0.5 to 1.0, corresponding to light travel times of 5 to 8 billion years, appeared approximately 25% fainter than they would in an empty, coasting universe. They were farther away than any model without dark energy predicted. The universe had not been decelerating under gravity's pull. It had been accelerating, pushing those ancient explosions to greater distances than expected. The statistical significance of this result grew as more supernovae were discovered. By 1998, each team had observed roughly 40 high redshift type Ia supernovae, enough to establish the acceleration with greater than 99% confidence. The systematic uncertainties, dust extinction, possible evolution in supernova properties over cosmic time, gravitational lensing effects, were carefully evaluated and found insufficient to explain the observations. Subsequent surveys have expanded the sample to thousands of type Ia supernovae spanning redshifts from 0.01 to beyond 2.0. The Sloan Digital Sky Survey discovered hundreds of intermediate redshift events. The Essence Project and the Supernova Legacy Survey added high redshift samples with improved photometric precision. The Hubble Space Telescope contributed the most distant observations, detecting supernovae so remote that their light began traveling when the universe was less than a quarter of its current age. These expanded datasets confirmed and refined the original discovery. The universe's expansion began accelerating approximately 5 billion years ago, when dark energy's repulsive effect overcame the gravitational attraction of matter. Before that transition, during the first 8 billion years of cosmic history, the expansion was indeed decelerating as matter's gravity slowed the outward rush. The supernovae at the highest redshifts, beyond 1.0, actually appear slightly brighter than the empty universe prediction, evidence of that earlier deceleration phase. The precision of modern supernova cosmology constrains the properties of dark energy itself. If dark energy's density remained constant over cosmic time, as expected for a cosmological constant, the expansion history would follow a specific curve. If dark energy's density evolved, strengthening or weakening as the universe aged, the curve would differ. Current observations favor a cosmological constant with remarkable precision, finding that dark energy's equation of state parameter lies within a few percent of -1, the value predicted for vacuum energy. The James Webb Space Telescope now extends supernova observations to even greater distances, detecting type Ia events at redshifts approaching 2.9 when the universe was only 2 billion years old. These observations probe the epoch before acceleration began, testing whether dark energy existed in the early universe or emerged later. The Vera C. Rubin Observatory, scheduled to begin operation soon, will discover hundreds of thousands of Type Ia supernovae over its 10-year survey, enabling measurements of dark energy's properties with unprecedented precision. Each distant explosion, each careful measurement of brightness and redshift adds another data point to humanity's understanding of cosmic acceleration, the thermonuclear destruction of white dwarfs billions of light-years away, events lasting mere seconds in cosmic terms, have revealed that the universe's fate depends not on the matter we can see, or even the dark matter we can infer, but on an energy that permeates empty space itself, pushing the cosmos toward an ever-accelerating expansion that will continue for eternity. The energy that permeates empty space operates through a mechanism that seems to defy ordinary intuition about how gravity and pressure interact. In everyday experience, pressure pushes outward. The air inside a balloon exerts force against the rubber. A compressed spring pushes back against whatever compressed it. But in the framework of general relativity, pressure contributes to gravity in ways that have no analog in Newtonian physics. And when that pressure becomes negative, the gravitational consequences reverse entirely. Einstein's field equations describe how matter and energy curve the fabric of space-time. And within these equations, both energy density and pressure appear as sources of gravitational attraction. For ordinary matter, this contribution from pressure is negligible. The pressure inside the Sun, enormous by human standards at 265 billion atmospheres at its core, contributes less than 1 part in a million to the Sun's gravitational field. But for a substance whose pressure is comparable in magnitude to its energy density, the pressure term becomes significant. And when that pressure is negative, when the substance has a tension rather than a push, the gravitational effect reverses from attraction to repulsion. Dark energy possesses precisely this property. Its equation of state, the relationship between its pressure and energy density, is characterized by a parameter designated W. For ordinary matter, W equals 0. Matter has energy density but negligible pressure. For radiation, W equals 1/3. Photons exert pressure equal to 1/3 their energy density. But for dark energy, observations constrain W to be very close to -1. Meaning its pressure is negative and equal in magnitude to its energy density. This negative pressure, when inserted into Einstein's equations, produces gravitational repulsion rather than attraction. The mechanism operates throughout all of space simultaneously. Unlike ordinary gravitational attraction, which weakens with distance according to the inverse square law, the repulsive effect of dark energy scales with distance itself. Two galaxies separated by 10 megaparsecs experience a repulsive acceleration from dark energy that is exactly twice as strong as two galaxies separated by 5 megaparsecs. This linear scaling means that while dark energy's effects are negligible on small scales, within galaxies, within galaxy clusters, they become dominant on the largest cosmic scales where the separation distances are measured in hundreds of megaparsecs. The energy density of dark energy has been measured through multiple independent methods to be approximately 6 times 10 to the -10th joules per cubic meter, equivalent to about 6.9 times 10 to the negative 27th kilograms per cubic meter when expressed as mass density through Einstein's famous equivalence. This is an extraordinarily small number. A cubic meter of dark energy contains less energy than a cubic meter of the best laboratory vacuum, which still contains residual particles and radiation. Yet because dark energy fills every cubic meter of the observable universe, its total contribution to cosmic dynamics is immense. The cosmological constant, designated by the Greek letter lambda, represents the simplest theoretical explanation for dark energy. Einstein himself introduced this term into his field equations in 1917, not to explain cosmic acceleration, which would not be discovered for another 8 decades, but to permit a static universe that neither expanded nor contracted. When Edwin Hubble discovered cosmic expansion in 1929, Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. But the mathematics never forgot. The term remained a valid solution to the field equations, waiting for observations that would demand its resurrection. In the modern interpretation, the cosmological constant represents a fundamental property of space-time itself, a vacuum energy that exists even in the complete absence of matter and radiation. Quantum field theory predicts that empty space should seethe with virtual particles, pairs of matter and antimatter that pop into existence and annihilate within the time permitted by the uncertainty principle. These virtual particles should contribute energy to the vacuum, and that energy should gravitate. The problem is that naive calculations of this vacuum energy yield values that exceed the observed dark energy density by a factor of 10 to the power of 120, one followed by 120 zeros. This discrepancy, the largest known disagreement between theoretical prediction and observation in all of physics, remains one of the deepest unsolved problems in fundamental science. The observed dark energy density has a curious property. It is comparable to the current matter density of the universe. Dark energy comprises approximately 68% of the total energy density, while matter, both ordinary and dark, comprises about 32%. This near equality seems remarkable because the two components evolve differently over cosmic time. As the universe expands, matter density decreases because the same amount of matter occupies an ever larger volume. But dark energy density, if it truly represents a cosmological constant, remains fixed, the same amount of energy per cubic meter regardless of how much the universe has expanded. This means that in the early universe, matter density was enormously higher than dark energy density. When the universe was 1/10 its current size, matter density was 1,000 times higher, completely dominating cosmic dynamics. When the universe was 1/100th its current size, matter density was 1,000,000 times higher. Dark energy was present, but utterly negligible. Only as expansion diluted matter density did dark energy gradually become significant. The two densities crossed approximately 5 billion years ago, when the universe was about 9 billion years old, and dark energy has dominated ever since. The transition from matter domination to dark energy domination marked a fundamental change in cosmic evolution. During matter domination, the universe's expansion was decelerating. Gravity from all the matter was slowing the expansion rate, even if not enough to halt it entirely. The deceleration parameter, designated Q, was positive. But as dark energy's repulsive gravity began to dominate, the deceleration decreased, passed through zero, and became negative, meaning the expansion began to accelerate. This transition occurred at a redshift of approximately 0.7, corresponding to light that has been traveling for about 6 billion years. The physics of negative pressure can be understood through a thought experiment involving a piston. Imagine a cylinder filled with dark energy, sealed by a movable piston. If you pulled the piston outward, increasing the volume, ordinary gas would do negative work. The gas pressure would resist the expansion, and you would have to supply energy to pull the piston. But dark energy has negative pressure, meaning it has tension rather than push. When you pull the piston outward, the dark energy does positive work on the piston. It helps the expansion rather than resisting it. And because energy is conserved, this positive work must come from somewhere. It comes from the creation of more dark energy to fill the new volume, maintaining the constant energy density. The more space expands, the more dark energy exists, and the more energy is available to drive further expansion. This self-reinforcing cycle explains why cosmic acceleration continues indefinitely once it begins. Unlike matter-driven expansion, which naturally decelerates as gravity acts, dark energy-driven expansion accelerates because the source of the acceleration, dark energy itself, increases as expansion proceeds. The universe is not merely coasting toward infinity. It is actively speeding up and will continue to speed up forever, assuming dark energy truly behaves as a cosmological constant. Alternative theories propose that dark energy might not be a cosmological constant, but rather a dynamic field that evolves over time. These theories, collectively called quintessence, posit a scalar field pervading space whose energy density and pressure can change as the universe ages. In some quintessence models, dark energy was even more negative in the past, leading to a W parameter less than -1, a condition called phantom energy that would eventually tear apart all structures in a Big Rip scenario. In other models, dark energy might decay in the far future, allowing matter to once again dominate and potentially reversing the acceleration. Current observations cannot definitively distinguish between a true cosmological constant and slowly evolving quintessence. The Dark Energy Survey, the Baryon Oscillation Spectroscopic Survey, and the Planck satellite have all constrained the equation of state parameter W to be within a few percent of -1, consistent with a cosmological constant, but not ruling out mild evolution. Future missions: the Euclid Space Telescope launched in 2023, the Nancy Grace Roman Space Telescope planned for later this decade, aim to measure W with sufficient precision to detect deviations from -1 at the percent level, potentially revealing whether dark energy is truly constant or dynamically evolving. The negative pressure that drives cosmic acceleration represents perhaps the most profound mystery in modern physics. It dominates the energy content of the universe, determines the ultimate fate of all cosmic structures, and yet its fundamental nature remains unknown. Whether it represents a property of space-time itself, the energy of quantum vacuum fluctuations, or an entirely new field pervading the cosmos, dark energy's repulsive gravity ensures that the universe will expand forever, carrying galaxies beyond each other's horizons into an increasingly cold, dark, and empty future. The components that shape cosmic destiny, ordinary matter, dark matter, and dark energy, combine within a mathematical framework that describes the universe's composition, geometry, and evolution with remarkable precision. This framework, known as the Lambda-CDM model, represents the standard cosmology of modern astrophysics, a set of 6 fundamental parameters that together account for observations spanning from the cosmic microwave background to the distribution of galaxies across billions of light years. Lambda, the Greek letter L, represents the cosmological constant, Einstein's mathematical term for a uniform energy density pervading all of space, now identified with dark energy. CDM stands for cold, dark matter, particles moving slowly compared to light when they decoupled from the primordial plasma, allowing them to clump gravitationally and seed the formation of cosmic structure. Together, these 2 invisible components dominate the universe's energy budget, with dark energy comprising approximately 68.3% and dark matter contributing roughly 26.8%, leaving ordinary baryonic matter, the atoms that form stars, planets, and living beings, at merely 4.9% of the total. The precision of these percentages emerges from decades of increasingly sophisticated observations, each measurement constraining the model's parameters from different angles. The cosmic microwave background provides the most stringent constraints, its temperature fluctuations encoding information about conditions when the universe was 380,000 years old. The Planck satellite, launched by the European Space Agency in 2009 and operating until 2013, measured these fluctuations across the entire sky with angular resolution of 5 arc-minutes and temperature sensitivity of millionths of a degree, producing the most detailed map of the early universe ever created. From Planck's data, cosmologists extract not just the relative abundances of matter and energy, but the universe's geometry, expansion rate, and the statistical properties of primordial density fluctuations. The Hubble constant, the current expansion rate, emerges as approximately 67.4 kilometers per second per megaparsec, meaning that for every million parsecs of distance, galaxies recede 67.4 kilometers per second faster. This value, derived from the early universe's physics, differs slightly from measurements using local distance indicators like Cepheid variables and type Ia supernovae, which yield values closer to 73 kilometers per second per megaparsec. This Hubble tension, as cosmologists call it, represents one of the most intriguing discrepancies in modern cosmology, potentially hinting at physics beyond the standard model. The universe's geometry, whether space curves back on itself like a sphere, extends infinitely flat like a plane, or curves outward like a saddle, depends on the total energy density compared to a critical value. Planck measurements indicate that the universe is flat to within 0.4%, meaning the total energy density equals the critical density to extraordinary precision. This flatness requires the sum of all components, dark energy, dark matter, and baryonic matter, to add to exactly 100% of critical density, a constraint that the measured values satisfy with impressive accuracy. The age of the universe follows directly from the expansion history encoded in lambda CDM parameters. Running the expansion backward, accounting for the changing dominance of radiation, matter, and dark energy at different epochs, yields an age of 13.787 billion years with an uncertainty of just 20 million years. This cosmic age agrees with independent estimates from the oldest known stars, white dwarf cooling curves, and radioactive decay of heavy elements produced in ancient supernovae, providing powerful confirmation that the model correctly describes cosmic evolution. Beyond the major components, lambda CDM includes parameters describing the primordial fluctuations that seeded all cosmic structure. The amplitude of these fluctuations, typically denoted sigma 8, measures the strength of density variations on scales of 8 megaparsecs, with Planck data indicating a value of approximately 0.811. The spectral index, denoted NS, describes how fluctuation strength varies with scale, with the measured value of 0.965 indicating slightly stronger fluctuations on larger scales. A prediction of inflationary cosmology that observations confirm. The optical depth to reionization, another lambda CDM parameter, encodes information about when the first stars and galaxies formed and began ionizing the neutral hydrogen that filled the universe after recombination. Planck measurements indicate an optical depth of approximately 0.054, corresponding to reionization occurring when the universe was roughly 700 million years old. This parameter affects the amplitude of CMB fluctuations on large angular scales, as photons scattering off free electrons during reionization partially erased primordial temperature variations. The success of lambda CDM extends far beyond fitting the cosmic microwave background. The model predicts the statistical distribution of galaxies across the sky, the abundance of galaxy clusters as a function of mass and redshift, the pattern of baryon acoustic oscillations imprinted in galaxy surveys, and the growth rate of cosmic structure over time. Each prediction has been tested against observations, and each test has confirmed the model's validity within measurement uncertainties. Baryon acoustic oscillations provide particularly elegant confirmation. These frozen sound waves from the early universe, with a characteristic scale of approximately 490 million light-years in today's expanded universe, appear in the clustering of galaxies measured by surveys like the Sloan Digital Sky Survey and the Dark Energy Survey. The scale serves as a standard ruler, its apparent size at different redshifts tracing the expansion history and confirming both the geometry and the dark energy content predicted by lambda CDM galaxy cluster abundances offer another test. The number of massive clusters that have formed by any given cosmic epoch depends sensitively on both the matter density and the amplitude of primordial fluctuations. Too much matter or too strong fluctuations would produce more clusters than observed. Too little would produce fewer. Surveys counting clusters through their X-ray emission, their gravitational lensing signatures, or the Sunyaev-Zeldovich effect, the distortion they imprint on CMB photons passing through their hot gas, consistently find abundances matching lambda CDM predictions. The model's parameters also predict the detailed shape of the matter-power spectrum, the mathematical function describing how density fluctuations distribute across different spatial scales. On large scales, fluctuations grow through gravitational instability at rates determined by the matter density. On small scales, the finite temperature of dark matter particles, when they decoupled from the primordial plasma, erases fluctuations below a characteristic mass scale. For cold dark matter, this cutoff occurs at masses far smaller than any galaxy, allowing structure to form hierarchically from the smallest scales upward. Observations of the Lyman alpha forest, absorption features in quasar spectra caused by intervening hydrogen clouds, probe the matter distribution on scales of megaparsecs, confirming the predicted power spectrum shape. Despite its successes, Lambda CDM leaves fundamental questions unanswered. The model describes what the universe contains, but not why these particular values. Why does dark energy density take a value so close to the matter density today, when these quantities scale differently with cosmic expansion and would have differed by factors of billions in the early universe? This cosmic coincidence problem suggests either extraordinary fine-tuning or some unknown mechanism linking dark energy to matter. The nature of dark matter remains unspecified within Lambda CDM. The model requires cold, collisionless particles that interact gravitationally, but not electromagnetically. Yet it says nothing about their mass, spin, or other particle physics properties. WIMPs, axions, and primordial black holes all satisfy the model's requirements, leaving the fundamental identity of 26.8% of the universe's energy content unknown. Similarly, Lambda CDM incorporates dark energy as a cosmological constant without explaining its origin. The quantum field theory prediction for vacuum energy density exceeds the observed value by 120 orders of magnitude, the largest discrepancy between theory and observation in all of physics. Either some unknown mechanism cancels almost all of this vacuum energy, leaving the tiny residual we observe, or dark energy arises from an entirely different source that mimics a cosmological constant. Small-scale challenges also persist. Simulations of Lambda CDM predict more satellite galaxies around systems like the Milky Way than observers find, though improved detection of ultra-faint dwarf galaxies has reduced this discrepancy. The predicted density profiles of dark matter halos, rising steeply toward galactic centers, appear steeper than observations of some dwarf galaxies suggest, though baryonic feedback processes may redistribute dark matter in ways that resolve this tension. These challenges drive ongoing research, with cosmologists testing whether modifications to Lambda CDM might better match observations. Perhaps dark matter particles interact weakly with themselves, allowing halos to develop less cuspy cores. Perhaps dark energy evolves over time, rather than remaining constant. Perhaps the initial fluctuations deviated from the simple power law spectrum that standard inflation predicts. Each possibility generates testable predictions that current and future observations will constrain. The Lambda CDM model, with its 6 parameters fit to exquisite precision, represents humanity's most complete description of the universe's contents and evolution. It explains how a nearly uniform primordial plasma evolved into the cosmic web of galaxies and voids we observe today, how the expansion rate changed from deceleration under matter's gravity to acceleration under dark energy's repulsion, and what the universe's ultimate fate will be as dark energy's dominance grows ever more complete. That growing dominance of dark energy, encoded in the lambda CDM parameters, determines not merely the universe's present state, but its ultimate thermodynamic destiny, a fate that unfolds across timescales so vast that the current age of the cosmos represents merely the opening moments of an essentially eternal future. The acceleration that began roughly 5 billion years ago will continue indefinitely, assuming dark energy maintains its current properties as a cosmological constant, with equation of state parameter W equal to -1. Under this assumption, the scale factor of the universe grows exponentially, doubling approximately every 10 billion years. After 100 billion years, the universe will be roughly 1,000 times larger than today. After 1 trillion years, the expansion factor reaches numbers that strain comprehension, 10 to the power of 43 times the current size. This relentless expansion carries profound consequences for the observable universe. Galaxies currently visible from Earth will gradually recede beyond the cosmic event horizon, the boundary beyond which light emitted today will never reach us, regardless of how long we wait. The Andromeda Galaxy, currently approaching the Milky Way at approximately 110 kilometers per second, will merge with our galaxy in roughly 4.5 billion years, forming a larger elliptical system, sometimes called Milkdromeda. But most other galaxies in the local group will eventually become unreachable, their light redshifted into invisibility as expansion carries them beyond the horizon. The cosmic event horizon in a dark, energy-dominated universe stabilizes at a fixed, proper distance of approximately 16 billion light-years. Objects currently within this radius will remain observable, though their light becomes increasingly red-shifted. Objects beyond this distance are already receding faster than light, not through motion through space, but through the expansion of space itself, and will never be seen regardless of how long future observers wait. The observable universe, rather than growing as more distant light reaches us, will actually shrink as expansion accelerates. Within the local group, gravitational binding holds galaxies together against cosmic expansion. The Milky Way, Andromeda, the Triangulum Galaxy, and approximately 80 smaller satellite galaxies occupy a region roughly 10 million light-years across, bound by their mutual gravitational attraction. This island of matter will persist as expansion carries all other structures beyond the horizon, leaving future observers in a universe that appears to contain only their local galaxy cluster, surrounded by an apparently empty void. The stars within this merged supergalaxy will continue burning for trillions of years, though the stellar population will change dramatically. The most massive stars, those exceeding 8 solar masses, exhaust their nuclear fuel within tens of millions of years, ending as supernovae that seed the interstellar medium with heavy elements. Sun-like stars persist for roughly 10 billion years before swelling into red giants and shedding their outer layers as planetary nebulae, leaving behind white dwarf remnants. But the smallest red dwarf stars, those with masses below roughly 0.25 solar masses, burn so slowly that their lifetimes exceed 10 trillion years, 1,000 times the current age of the universe. These dim red dwarfs, currently the most numerous stars in the galaxy, will dominate the stellar population as larger stars die. Proxima Centauri, the closest star to the Sun at 4.24 light-years distance, burns hydrogen so efficiently that it will continue shining for approximately 4 trillion years. Stars even smaller approach theoretical lifetimes of 10 to 20 trillion years, their cores slowly converting hydrogen to helium at rates that make the Sun's fusion seem profligate. But even these cosmic mazes eventually exhaust their fuel. By roughly 100 trillion years from now, 10 to the power of 14 years, the last conventional stars will have burned out. The universe enters what cosmologists call the degenerate era, populated by the cooling remnants of stellar evolution. White dwarfs, neutron stars, and black holes, along with planets, asteroids, and diffuse gas that never achieved stellar ignition. White dwarfs, the carbon-oxygen cores left behind when sun-like stars shed their outer layers, begin their existence with surface temperatures around 100,000 Kelvin. They possess no internal energy source, radiating away their residual heat over time scales that dwarf stellar lifetimes. A white dwarf cools to the temperature of the cosmic microwave background, currently 2.7 Kelvin, but decreasing as expansion stretches the background radiation, within roughly 10 to the power of 15 years, becoming a black dwarf, an object so cold it emits essentially no radiation. Neutron stars, the ultra-dense remnants of massive star supernovae, follow similar cooling trajectories. Born with surface temperatures exceeding 1 million Kelvin, they radiate energy through neutrino emission and photon radiation, cooling to background temperatures within comparable timescales. Their immense densities, roughly 10 to the power of 17 kilograms per cubic meter, equivalent to compressing a mountain into a sugar cube, persist indefinitely, supported by neutron degeneracy pressure against gravitational collapse. The thermodynamic arrow points inexorably toward equilibrium. Every temperature difference represents a potential for energy flow, and every energy flow increases the universe's total entropy. Stars convert gravitational potential energy and nuclear binding energy into radiation, which redshifts into ever longer wavelengths as expansion stretches space-time. The cosmic microwave background, already cooled from 3000 Kelvin at recombination to 2.7 Kelvin today, will continue cooling inversely with the scale factor, approaching but never quite reaching absolute zero. Black holes paradoxically represent the highest entropy objects in the universe for their given mass. A stellar mass black hole of 10 solar masses possesses entropy roughly 10 to the power of 78 in natural units, vastly exceeding the entropy of the star that formed it. Supermassive black holes like Sagittarius A star, with 4 million solar masses, contain entropy approaching 10 to the power of 90. These objects dominate the universe's entropy budget, and their eventual fate determines the ultimate thermodynamic destiny. Stephen Hawking's 1974 discovery that black holes radiate thermally revolutionized understanding of their long-term evolution. Quantum effects near the event horizon produce particle-antiparticle pairs, with one member occasionally escaping as Hawking radiation while the other falls inward, effectively extracting mass from the black hole. The temperature of this radiation varies inversely with mass, A solar mass black hole radiates at roughly 60 nanokelvin, while a supermassive black hole of 1 billion solar masses radiates at merely 60 femtokelvin, far colder than any natural environment. This radiation proceeds extraordinarily slowly. A stellar mass black hole requires roughly 10 to the power of 67 years to evaporate completely, a timescale that makes the current age of the universe seem instantaneous. Supermassive black holes persist even longer, with evaporation time scaling as mass cubed. A black hole of 1 billion solar masses requires approximately 10 to the power of 100 years to radiate away entirely, ending in a final burst of high-energy particles as the last remnants evaporate